Good morning, everyone. This is Han Hu from Microsoft Research Asia. The title of this talk is Swin Transformer and 5 Reasons to Use Transformer and Attention in Computer Vision. Now, everybody knows transformers. It was invented 4 years ago. During the last 4 years, it has refreshed the NLP field and is also the current dominant architecture in this field. It's so successful in NLP, encouraging researchers to think about a question: what is the role of transformer for computer vision? Let me directly pose the answer. We think it will also refresh and dominate computer vision. We are confident on this answer because transformers have achieved very strong performance on 3 important vision benchmarks since the end of the last year. Let's say the first benchmark, ImageNet 1000 image classification. This task is the most important benchmark in computer vision to the date. The task is to categorize images into 1000 classes. This figure shows the best methods across years. Before the last October, all methods are based on a thin backbone. Now, transformer architecture surpasses all previous approaches, concretely by VIT from Google. Now, most top methods are based on transformer architecture. What is VIT? Please see this illustration. It's very simple. An image is first partitioned into 16 by 16 patches. Then, a standard transformer architecture is applied on these patch features. The transformer encoder is almost unchanged from that used in NLP, with the same depth, same number of channels, and the same number of heads. Though very straightforward and simple, the performance is very strong. It performs the state-of-art at the time. It's also the leading algorithm and the ImageNet 1000 benchmark to the date. Well, ImageNet 1000 image classification is an image level task. Let's say 2 other most important vision benchmarks at region level and pixel level. Firstly, Cocoa object detection, a task to produce the location of objects in image. This figure shows the best methods across years. Before this March, all methods are based on a single backbone. Now, transformer backbone surpasses all previous approaches, concretely by Swin transformer. Now, all top methods are based on Swin transformer. Let's say another benchmark about segmentation, a task to produce predictions for every pixel. Also, before this year, all methods are based on a single backbone. Now, transform backbone surpasses all previous approaches by a large margin, concretely by a Swin transformer also. So, what is Swin transformer? It's basically an architecture which introduces some good priors for visual signals into the standard transformer architectures. The good priors include hierarchy, locality, and translation invariance. Both the ideas of Swin transformer and VIT are very simple. However, the road towards these architectures takes 4 years. In fact, soon after transformer was invented in the NLP field 4 years ago, the computer vision community has started to tame this architecture for computer vision. Or more concretely, the community discovered more and more merits of this architecture year by year. The first 2 merits being explored is the general modeling capability of this architecture and the complementary of transformers or attention layers to convolution layers. These two methods are first explored in two parallel works in November of 2017. The third merit is its strong modeling power explored since April 2019. The fourth merit is that it can benefit the collection of vision and language, which was explored since early this year. The fifth merit lies in its ability to be scaled up in both model size and data size. In the following, I will describe these 5 reasons more detailedly, as well as introduce related works. In particular, I will also introduce Swin transformer in detail, which is a general-purpose backbone for computer vision. It basically exploits the third merit of transformer. Let's go to the fourth reason to use transformer in computer vision. That transformer owns general modeling capability. In fact, transformers can be treated as a general graph, where all concepts and their relationships can be modeled by a graph. The concepts can be either concrete or abstract. The general modeling capability is also partly ascribed to the verification principle in building relationships between graph nodes. Please see the right illustration. Thanks to the verification philosophy, transformers can process image patches of different scales and even process multi-model data such as text and images. This general capability enables transformers to model all kinds of relationships in computer vision, such as pixel-to-pixel, object-to-pixel, and object-to-object relationship, which cover almost all vision applications. Here is a pioneer work in CPR 2018. The work aims to model the relationship between objects. Please see this image patch. I believe it's difficult to figure out what it is by seeing this patch alone. However, if we see the context, it's easy to recognize the patch as a baseball glove. After we note there is a baseball player holding it. In previous years, there are no good networks to model this kind of relationships. However, the self-attention module in transformer can be leveraged to conveniently and effectively model this relationship. Please see this illustration. The input and the output of this module have the same dimension, and this module can thus be applied in place in many places of a network. We also made some adaptations. For example, we additionally account for the relative position in attention computation, which is proved important in the object detection application. This module also helps to create the first fully end-to-end object detector. Concretely, the module is inserted into 2 steps of a fast-acting object detector. Please see the red blocks in this pipeline. Firstly, it's inserted in the instance recognition head. Now, the objects can be jointly recognized instead of processed separately as in previous methods. The second is to do duplicate removal. In previous methods, duplicate removal is usually achieved by a handcrafted non-maximum suppression method. By this self-attention module, we can make this step end-to-end learnable. Another work I would like to mention is from Facebook AI Research called DTR. It directly applies the encoder-decoder architecture of transformer to the object detection problem, which is also an end-to-end object detector. Next, we introduce the second reason to use transformer in computer vision. That is, the transformer layer or attention layer is complementary to convolution layers. Convolution is criticized as being too local, that the convolution layer has difficulty extracting long-range pixel-to-pixel dependency. Please see this illustration. For this output, even by stacking 4 zeros, only pixels within a very short distance are modeled. Other pixels are not. The transformer layer is complementary to this local convolution layer, that it can see all input nodes by a single layer. A pioneer work is Nanoko networks, proposed on COPR 2018. It applies self-attention modules to encode dependency between distant pixels in complementary to the local convolution layers. Please see this illustration. A football pixel and the human body pixels are distant from each other. Their dependency is hard to be captured by convolution networks. Nevertheless, it can be conveniently modeled by a single self-attention module. In its work, the self-attention modules are sparsely inserted into a ResNet to complement the local convolution layers. For example, this is a ResNet. In object detection, one block is inserted at the stage 4 of the ResNet. The Nanoko network is very successful. It can broadly improve existing action regulation, object detection, and semantic segmentation algorithms. In common understanding, the self-attention formulation models pairwise relationship, for example, the dependency between pixel pairs. To learn meaningful pairwise dependency, we expect different query points affected by different key points. This is an illustration. The left image shows 2 query pixels at different locations. A red query is on a car, and a yellow query is on a fire hydrant. The right image shows some key points colored in green. We expect the car query pixel mainly affected by these 2 key points, and we expect the fire hydrant query pixel mainly affected by these 2 different key pixels. But what does the self-attention module really learn? Unlike expected, we find different queries in the left image are usually affected by the same key pixels in the right image. This means the self-attention module degenerates from query dependent to query independent. It behaves more like a unary model instead of a pairwise model. We show some real examples from the tasks of object detection and semantic segmentation. These images are the attention maps of all key pixels to different query points, where the query points are marked by the white crosses. And for the attention maps, the warmer the color is, the higher the attention similarity is. We can see that the attention maps of different query points are very similar, especially for object detection. This also indicates that the self-attention model degenerates to a unary model. We found this degeneration phenomenon in 2019. This phenomenon also indicates that the Nanoko block can be simplified by explicitly leveraging the degenerated formulation. Hence, we propose GC block, which reduces 2000 times computation and 20 times module size compared to Nanoko networks, where the accuracy is unchanged on Coco object detection. We further study the reason leading to this degeneration phenomena and propose a disentangled self-attention module to address this issue. Next, let me show the third reason to use transformer. That is, transformer's strong modeling power due to adaptive computation. The convolution layer is criticized to have low efficiency. In fact, convolution performs a template matching using fixed filters across all image positions. Please see this image. There are 3 boards with slightly different head poses. With a convolution layer, we need 3 channels to encode these 3 board heads, which is inefficient. Other than using fixed filters across image positions, transformer layer uses adaptive filters with the filter width determined by composability of 2 pixels. In this way, potentially we need only 1 channel to model different board head poses. This merit encourages training transformer as a backbone for computer vision. If succeed, the impact to the vision field will be very significant, as the vision backbone is used in almost all vision tasks. The first attempt was made in 2019. The most popular backbone network in computer vision is ResNet at the time. We replace all convolution layers in ResNet with transformer layers, maintaining the same computation complexity. The resulting network is called local region networks. Here, we compare this network with ResNet on ImageNet classification. The blue curve shows the results of ResNet, which is based on convolution layers. The orange curve shows the results of our local region networks. The transformer-based local region network is 2.7% better than ResNet. However, though theoretically the same efficient than ResNet, it's much slower in real usage. A main reason is that different queries use different case sets, which is unfriendly to memory access. Please see this illustration. For the center point Q, we use all pixels inside this red window as keys. For a query at another location, for example Q prime, the window will be changed to centering on this new query. Because Q and Q prime use different case sets, the real speed of this approach is limited. Because of this, it's not practical to work as a backbone. The situation was changed by a milestone work from Google, VIT, as we have introduced at the beginning. In addition to the impressive results on image classification, it has another interesting behavior. Please see this table. On a TPU, it's even 50% faster than the ResNet with similar flops. We find the main reason of its fast real speed is that the self-attention computation is performed globally, and thus all queries share the same case sets. However, this approach doesn't consider the good priors in computer vision, and we argue it could be suboptimal for computer vision applications. We thus consider introducing good priors of computer vision into the architecture design, and the resulting architecture is called Swin transformer. Swin transformer basically equals transformer plus good priors for visual modeling, such as hierarchy, locality, and translational invariance. Please see this illustration. It's a standard transformer architecture used in VIT. In this illustration, each gray box indicates the image patch, and the red window indicates the scope of self-attention computation. In VIT, the computation is performed globally over an entire image. In Swin transformer, we introduce several priors, which will be discussed one by one in the following slides. The first good prior is called hierarchy. Please see the left figure. In computer vision, no matter how large a fat cat is, it's still a fat cat. The vision algorithms are usually required to process these objects of different scales. This goal can be well achieved by a hierarchical structure. Please see the right figure. It starts with smaller image patches, for example 4x4, and builds hierarchical feature maps by merging image patches in deeper layers. The second good prior is called locality. Different from natural language, visual signals are highly correlated in spatial. Locality has proven very beneficial in modeling such high correlation data. Locality can also make the complexity linear to image resolution, instead of quadratic as in VIT. For example, please see the left image. There are 256 patches, and the computation of VIT is in quadratic complexity with respect to the number of patches. Please see the right image. When we partition an image into 4x4 windows and perform computation within each window, the complexity will be reduced by 16 times. An important feature of our locality is that the windows are non-overlapped. This design ensures our fast speed in real computation, particularly when compared to the traditional standing window approach. Please see this illustration. The left figure shows the locality by standing window. As we discussed before, different queries have different key sets, which is friendly to memory access, and the real speed is thus not good. The right figure shows the illustration of our non-overlapping windows. Different queries within a same window will share a same key set, and is 3 times faster in real speed. Another important feature is that we enable cross-window connection by shifting window partitioning in successive attention layers. This makes this approach as effective as the standing window methods, or even better due to regularization effects. The third good prior is called translational invariance. In computer vision, we expect a fat cat at arbitrary location is recognized as a fat cat. Moreover, relative position bias plays a more important role in vision than in NLP. We implement this prior by adding a bias term to the similarity computation. An interesting point here is that we don't guarantee fully translational invariance due to long overlapped windows. We call it translational semi-invariance. Interestingly, we find this semi-invariance performs as good as fully translational invariance in experiments. Based on these good priors for computer vision, we design the architecture of Swin transformer as shown in this figure. It basically follows ResNet to have 4 stages, with each stage the same resolution as that of ResNet, to facilitate application to downstream tasks. In each stage, there are repeating Swin blocks, with each block the same as that of transformer architecture, but with attention computation limited within each shifted window. Since backbone networks are required by almost all vision tasks, Swin transformer can be applied to various visual applications. We demonstrate its power on several common benchmarks. The first is object detection and instrumentation on COCO. Previously, the best approach is efficient det plus copy-paste, published on this year's COPR. Now, all the top 3 records of this benchmark is built on Swin transformer. The current best record is 60.6 MAP, which is 3.5 higher than that by copy-paste. For instrumentation, the best record is 52.4 MAP by Swin transformer, which is 3.3 higher than previous best record by same models. The improvements over previous backbones are universal. For example, on these 4 detection methods and 3 different model sets, transformer performs consistently 3 to 4.5 points over ResNet with similar model size and computation. The second application is semantic simulation on ADE20K. It also surpasses all previous models by a large margin. That is, this model is 5.5 higher than the previous best-selling model. On ImageNet 1000 image classification, although VIT is leading the leaderboard, Swin transformer is 3.5 points better than VIT with similar model size, computation, and pre-trained dataset. Swin transformer not only works well on images, it's also good for videos. We extend the Swin transformer as a video backbone by introducing an additional time dimension. And 2 major video benchmarks, Kinetics 400 and Kinetics 600, Swin transformer achieves SOTA, surpassing previous best method Vivid by a large margin when using the same pre-training data. On Kinetics 400, it achieves 84.9, which is 3.6 better than Vivid. On Kinetics 600, it achieves 85.9, which is 2.9 better than Vivid. Let's go to the last 2 reasons to use transformer in computer vision. The first reason is that using transformer where net vision part has similar architecture as net of language part. It will benefit visual language learning as illustrated in this OpenAI's work clip, where VIT performs better than net of ResNet and similar computations. The fifth reason is that the vision transformer seems able to be scaled up to very large model and very large data. In fact, a work publicly available just 1 week ago by Google has demonstrated a 2 billion model to perform state-of-the-art on ImageNet 1000 image classification. Finally, here is a summarization of this talk. Since the invention of transformer in the NLP field 4 years ago, it has quickly dominated the NLP field in architecture design. In computer vision, the power of transformer was gradually unleashed during the last 4 years by exploiting 5 merits of transformers. The first merit lies in the general modeling capability. I list here 6 related works which explore transformer or attention layers for visual relationship modeling. These papers marked in red are the works of ourselves. The second merit is the ability to complement convolution, which is too local. I list 3 related papers here which exploit this merit. The third merit is its strong modeling power. This merit encourages stronger transformer backbone than convolution backbones, typically include VIT and Swin transformer. The fourth reason is that it can benefit collection of vision and language due to unified modeling. The fifth reason is the ability to be scaled up in both model size and data size. Given these strong 5 reasons, we believe that transformer will also refresh and dominate computer vision, like what has been observed in the field of natural language processing. This is the end of this talk. Due to having used up my assigned time, I will skip the voice Q&A session. If you have questions, please post them in the message channel. I will respond to you in that channel. Also note, this is not a survey. There are many great works related but not mentioned in this talk. I feel sorry about that. Thanks for your attention.
Okay, thank you, Han, for the great talk and great work. So there are a few questions from the audiences. First, one question from the YouTube channel basically says, in certain vision tasks, I think focusing on local features rather than modeling the entire relations helps a lot. And then transformer seems to be quite efficient in this way. So is there any personal preference or future works you have in mind for satisfying the input for transformers?
Yeah, I think this is a very good proposal. Actually, I think a recent trend of studying transformer in convolution is right. What you mentioned, that the community want to use transformer as a vision backbone, but not only complement to convolution. So in this talk, Swin is just I think it is one exploration of this direction, and also there are many other attempts. Yeah, if you care about recent some recent works, you will see many modifications to perform transformer locally to replace convolution networks. Yeah.
Okay. So there are also two questions from the Zoom. Maybe. So the first one is, can we say multi-head self-attention is equivalent or better combination of large kernel convolution plus dynamic convolution and group convolution? Yeah.
Yeah, I partly agree your viewpoint. Yeah, transformer it has many merits, and one of the merit is that it has a very strong modeling power, and this power comes from dynamic convolution. I mean dynamic computation. So for this merit, it's very similar to dynamic conv, but I think transformer has better potential because it uses verification principle to model the relationship between different nodes. So I think it has better potential. Yeah. Hi.
Oh, shit. Sorry. So it seems Swin transformer papers still use convolution in decoder. What do you think of using Swin blocks for encoder and decoder, like the Swin ULET?
Yeah. Because Swin transformer focus on backbone, so it doesn't change the decoder part. So it can it can be combined with transformer decoder and also some traditional decoder. So yeah, this is my answer.
Okay. Yeah, sounds good. Maybe final one questions from me. So you see, you have some nice experiments on the GC that's simplifying the self-attention. The finding is also very interesting. So do you see similar findings in the vision transformer, or do you think the self-attention there can be simplified in a similar way as well?
Okay, this is a very good question. We didn't find the same phenomena in vision transformers. I think one reason probably is that so in vision transformer or in Swin transformer, the number of the nodes is not very large. So we didn't observe the same phenomena as for local networks. Yeah.
Okay. Yeah, sounds good. Thank you for the great talk. So we have the next talk from Zhuowen too, from UC San Diego. So it will be on beyond bounding box structure detection with transformers.
Hello, everyone. This is Zhuowen.
Sorry, let me reshare something. Oh, okay, I think it works.
The title for my talk is Beyond Bounding Box Structure Detection with Transformers. The main theme of the tutorial is representation learning via graph structured networks. I'll be focusing on transformers, which are also graphs, but a special kind. Transformers have received a lot of attention lately and have been widely adopted in natural language processing, computer vision, and beyond. We'll first talk about one of our CVPR 2021 papers, line segment detection using transformers without edges. Line segment detection has been a long-standing problem in computer vision, and it is a building block for many downstream computer vision tasks. We will see how transformers can be used to detect geometric structures like line segments. Next, we will discuss our ICLR 2021 paper that learns a constellation net model for few-shot learning with self-attention operated on the learned object parts. We will then go over another paper of ours at CVPR 2021 for pose recognition using transformers. Here, the key points for the individual persons are to be detected. And the key points are another type of geometric structures of interest. We will then conclude. We probably don't need to say too much about convolutional neural networks that have been widely adopted in our field. They have a lot of desirable attributes for computer vision tasks, including learnable features, fusion, fitting, estimation, etc. For object detection and instance segmentation, with the CNNs, a standard pipeline such as FastRCN can be viewed as consisting of two basic modules, an encoder and a decoder. The encoder extracts image features, and the decoder performs inference and prediction for the individual objects. Transformers were introduced by Vaswani et al. In 2017, and transformers have since then had an explosive development. Transformers have emerged as another deep learning backbone for representation learning and inference. Typically in NLP, a transformer consists of an encoder and a decoder in translation to translate an input sequence of one language to a sentence of a different language. On the right, it shows the backbone for the transformer consisting of layers of attention modules. On the left, it shows a transformer encoder for a sequence of input. A transformer builds a self-attention layer followed by feed-forward networks and other components. The main formulation in transformer is the self-attention mechanism, which can be viewed as learnable operations on a fully connected graph of all pairs. On the right, it shows a zoom-in version for the self-attention layer. It is now from top to bottom. The input sequence consists of two words here, thinking machines. They're called tokens. Each token in the input sequence is represented as an embedding, which is learnable. There are three mappings to be learned to map the token embedding into queries, keys, and the values. For a token of current focus, for example, thinking, the similarity between its query Q1 with every key will be computed, including itself. So here Q1 dot product with K1 equals 112. And the Q1 dot product with K2 equals 96. Then the similarities will be normalized using a soft max function. So then after normalization, the weight for Q1 K1 is 0.88, and the weight for Q1 K2 is 0.12. And these weights then will be used to weight their values to compute an update output for the token. Here Z1 equals 0.88 times V1 plus 0.12 times V2. On the left, two attention maps for two different attention heads at different layers are shown. We can see connections for different tokens learned at different layers. In a sense, these are also learned graph structures in transformers. There has been an explosive development of transformers in the field. The self-attention mechanism in transformers generates a special graph that is fully connected between every pair of tokens or nodes. Transformer has enriched the modeling power to capture the contextual dependency between the nodes. Spatial correlation can be naturally incorporated using positional embedding or positional encoding. Some notable developments in transformers include transformer, BERT, GPT, GPT-1, GPT-2, GPT-3, Theta, and the VIT, and now subsequent works. So now, let's discuss the paper, Line Segment Detection Using Transformers Without Edges by Yifan Xu, Weijian Xu, David Chan, and myself. In David Marr's theory, Marr laid out a foundation for visual inference by performing a sequence of steps from low level, middle level to high level process. Given an input image, an edge map is first extracted. And then a 2.5D sketch map are extracted, which are further grouped into 3D model representation for object detection and reconstruction. This pipeline by Marr is intuitive and has inspired many works in computer vision. However, a major limitation in this pipeline is that the system requires near perfect solution in every stage, which is hard to achieve in practice. In the deep learning era, David Marr's theory has been realized using a sequence of CNN-based modules. A typical work, such as the one shown here by Zhou et al., extracts edges, junctions, depth maps, followed by inference and grouping process. However, it consists of many steps with heuristic designs in the inference and grouping process, which are difficult to implement, adapt, and integrate into other pipelines. They also consist of accumulated errors. So here, we want to simplify the line segment detection pipeline by performing line segment detection directly as an object detection task with a single process. A naive solution could be simply done by treating line segments as objects and solve it using a standard object detector such as FastRCN. For FastRCN, it typically consists of predefined anchors for the possible bounding box hypothesis. However, line segments are atypical objects that do not observe regular aspect ratios. For example, here we show 3 extreme cases for line segments that do not fit into the regular anchors: a short line, a near horizontal line, and then a near vertical line. They're hard to be covered by limited choices of predefined anchors. So in our ablation study, we will see that treating line segments as standard objects using fast RCN will lead to a suboptimal solution. The Datter paper, end-to-end object detection with the transformer, is a seminal work performing set-wise object detection using transformers by removing the predefined anchors and post-processing steps such as non-maximum suppression. It also has a special design of object queries or hypotheses that are seamlessly integrated into the Datter decoder. The main difference between Datter and RCN family models is that now Datter skips the sliding window strategy and performs learning and inference for all the objects all together. Motivated by the success of Datter, we apply transformers to tackle the line segment detection problem. We call our algorithm line segment detection using transformer or ladder. We cast line segment detection in a holistically end-to-end fashion without explicit edge, junction, or region detection, and the heuristics-guided perceptual grouping process. It is different from the existing literature in this domain. We perform line segment detection using transformers, specifically based on Datter. But different from Datter, we formulate the training objective using a direct endpoint loss that overcomes the bounding box-based limitations that are not suitable for general geometric structures such as line segments. Here, it shows the pipeline for our ladder algorithm. The image features for an input image are first obtained using CNN network, which are then fed into an encoder for further representation learning, and then followed by a decoder to perform line segment detection directly. Here, we show detailed illustration for a ladder. We perform line segment detection under a direct endpoint distance loss. This loss term is particularly suitable for detecting geometric structures such as line segments that are not conveniently represented by the standard bounding box representation. The training objective consists of 2 losses. The classification loss for a query being a line or background, and the distance loss to the ground truth line segments. So ladder consists of 3 key elements: line segment detection directly in a single step without edge or junction extraction, transformer-based decoder for set detection, and the coarse-to-fine multi-scale design. For a given image, the CNN features are first extracted, added together with the position encoding, and then they are sent as an input to a coarse encoder. The output for the coarse encoder are used as a memory for the coarse decoder based on the initial line queries. And then the output for the coarse decoder are the input for a fine decoder, which use the output for a fine level encoder. So our ladder consists of 2 decoder and encoder strategy, 1 coarse level and 1 fine level. And the end result will be the detect line segments all together. The transformers learn to gradually refine line segments through layers of self-attention mechanism. This line shows detect line segments at different layers. And this line shows the overall overlaid attention maps in the decoder. And then the numbers are shown below for each layer. For ladder, its coarse layer 1 already has a decent localization for the line segments. And the further layers in transformers help refine the detection. We also show 3 line segment queries for 3 different images. 2 interesting observations can be made. 1, the exact location for the same query varies from image to image. 2, each line query is dedicated to a certain area in the image. So in terms of this, line queries are variant, but also they are consistent. We also show an ablation study if one would directly adopt faster RCN and the data to perform bounding box-based detection. Latter shows its advantage due to its direct endpoint loss. So the faster RCN here treats each line segment as an object. And the vanilla data also uses bounding box representation, and we apply it directly to detecting line segments. And ladder has a better performance than faster RCN and the vanilla data using bounding box representation. The elongated geometric structure for line segments make it difficult for the standard bounding box representation to formulate. And here we show more comparison between ladder and the existing methods. The wireframe dataset and the York urban dataset with the quantitative measures. Ladder achieved competitive results when compared to the existing approaches. And here we show quantitative comparison between ladder and some existing approaches. Overall, ladder shows a cleaner solution than the other method. So to recap, our line segment detection transformer method, ladder, formulates line segment extraction as a direct object detection problem. Ladder overcomes the limitations in the standard geometric structure detection system that consists of separate edge junction extraction and a heuristic-driven perceptual grouping process. The direct endpoint distance loss devised in ladder point to a promising direction in set prediction beyond the standard bounding box representations. Now, let's discuss our iClear 2021 paper, Constellation Nets for Few-Shot Learning by Weijian Xu, Yifan Xu, Huajin Wang, and myself. Constellation models, basically graphs built on parts, have had a long history in computer vision. Here we show 3 constellation models: the pictorial structure by Fisher and triangular flexible constellations of parts by Fergus et al., and part-based graphical models by Sudeth et al. We also list some other constellation family models. There are more that are not included. Here, we focus on a few-shot learning scenario. A typical few-shot learning situation has few-shot classes that consists of much less images than the basic classes. In the few-shot learning scenario where training data is scarce and generalization is needed, the representation part of CNN no longer suffice. In this work, we introduced the constellation concept to CNNs by learning an integrated part-based model together with the CNN representation. The key is to building an explicit part-based model with self-attention that captures the appearance and the spatial configuration of the object parts. Once the CNN features are computed, a soft K-means algorithm is performed to learn the clusters. For each cell, the distance map to the cluster center are computed. They're considered as the code word. And then adding the distance map with position encoding will be the input for our self-attention union that models the parts and their configurations jointly. Note in this scenario, the image level classification is learned in a supervised way, but the parts and their spatial configuration are learned in an unsupervised way. By building recursive convolution and constellation model, our model captures both the implicit and explicit object part representation that are important in a few-shot learning situation. Here, it shows the detailed self-attention module that captures the part relations. The cell CNN features are clustered first. Then the distance map to the cluster centers are computed and added with the position embedding. This allows for the modeling for both abstract appearance and the spatial configuration for their parts. The output of this unit will be sent back to the main CNN backbone as an additional enriched feature. The overall constellation net model can be learned in an integrated fashion. Here we show quantitative comparison of constellation net when compared with the existing literature. We show visualizations for learned clusters and the parts. Again, these parts are learned in an unsupervised way. Throughout the layer, we can see consistent parts that are being able to extract it or learn in the network. Here, we also visualize attention maps for some examples. For query position, its corresponding attention maps to the keys are demonstrated. We can see the semantic connection between the query and the other parts or other areas in the image. So the self-attention learns the joint appearance and spatial configuration for the object parts. So to recap, we have developed a constellation net for few-shot learning using self-attention on learned codebook with positional embedding. Constellation net captures the rich appearance and the spatial configuration for the object parts that generalize well to the few-shot learning scenario. The self-attention mechanism provides an effective and efficient means to capture the graph structure of object parts that are beyond the previous literature in constellation models. Next, we will go over our post-recognition with cascade transformer paper by Kelly, Zhuowen, Xiaolong, Yifan Xu, Weizhen Xu, and myself. In this work, we tackle the post-recognition problem in a regression formulation. In a typical post-recognition task, the individual person and their key points are to be detected. We present two model variants, a two-stage system and an end-to-end framework. There are typically two families of approaches in pose recognition. One is based on heat map, which performs dense classification for the points, then with clusters, and then the heat map generate, and also subsequent process and grouping. Another line of work is regression-based, which performs key point regression directly. Typically, heat map-based approaches attain higher scores than regression-based ones. But regression-based ones still have nice properties, being simpler and direct. Motivated by this, we design post-regression transformers, a two-stage and end-to-end model. So here, it shows a two-stage system. Given an image, we first learn a database transformer to detect persons, in all persons in the image. Then for each detected person, we would crop its image patch and then train a second transformer that performs key point detection directly. So here, key points are another type of geometric structures that need to be detected all together. The system consists of two stages that are not end-to-end trained for the separate stages. And we also provide another variant, which is end-to-end. It also performs person detection, but once it's detected, instead of cropping the images, it would use a spatial transformer network to localize the areas of interest, and then based on another transformer, it will extract the control points. So the slide here shows the results by our proposed method. So here it shows the visualization for extract key points at different layers. You can see the process of refining the key points. We also visualize queries for the different control points. There's a bias for the localization for the specific queries. Certain queries are dedicated for certain control points. The learned key point queries are biased, and transformer decoder is a general inference machine performing regression for the key points for a pose. Here we show more illustrations with the visual results. To recap, post-regression transformer is a direct regression-based method for pose recognition without heuristics guided pre or post-processing. And the transformer decoder can be viewed as a general purpose inference machine. To conclude, transformer as a dense graph, transformer-based representation provides an effective way to model the joint image relations and the rich spatial configuration. Positional embedding or positional encoding adopted in self-attention provides a powerful means for capturing the complex spatial relations. Detection transformer or DATR by Carrion et al. Perform set detection by removing limitations, for example, predefined anchors and non-maximum expressions in the previous sliding window-based object detection approaches. Using a direct geometric loss under DATR points to a promising direction for geometric structure extraction that is beyond the standard bounding box assumption in the standard object detection frameworks. Thank you.
Okay. Thank you, Zhuowen, for the great talk. So if you have any questions, you can post uh, in the channel, in the chat, or in the YouTube channel. So Zhuowen is here to answer the questions. So maybe while you are writing up the questions, I have maybe one or two from myself. So in the last work on the post estimation, you are doing regression style, and then that's very direct and simple. But as you mentioned, you're still not doing as good performance as the heat map style. So do you have any comments on like extending like similar framework to the heat map style post estimation?
Yeah, thanks, Xiaolong. That's a great question. Yeah, you're right. So somehow this makes us to rethink about the potential for transformers and think of transformers like in the regression scenario. It is particularly suitable for, let's say, performing essentially a Bayesian inference, but you can consider these are like a sequence. It's a little bit like a MCMC type of thing, but of course with a more deterministic design. But somehow this regression based on the previous one still might miss some key areas where dense detection would cover completely, because dense detection can almost cover everything, then perform aggregatization, where transformers is just every time it's regression, then regression, or estimation, then hopefully we can land at a better location. And by transformers itself, because it's basically it's a self-attention unit, has a better capability in putting everything together globally, which was previously difficult in a heat map base. Kind of in the future, I think these two directions do need to meet each other, taking advantage from both sides. You asked a great question that unfortunately I don't have a direct answer to it. Otherwise, I will be writing another paper on it.
Mm-hmm. Thank you. So it seems like in also the segment detection and also the proposed estimation, you're still using the conflict to extract the features. So any plans on extending it to just all using vision transformer for this kind of work?
Yeah, that's a great question. So actually coming back to the point by Han Hu, and I somehow have a different view.
Mm.
So for vision transformers, we have seen its performance, but on the other hand, CNNs are still good at certain things, and then its computation is still relatively more efficient. So I feel like in the long run, we should use transformers to do things that CNNs cannot do. Maybe for extracting some local features, CNNs may not be maybe already good enough. So I think that these great points need to be evaluated. So here, I'm not too obsessed by changing completely things by transformers. We should use transformers in a wise way to best use transformers to certain areas, not to completely replace CNNs by transformers. That's my personal view.
Hmm. Yeah, that's interesting, because everyone is like, we should replace everything with transformers. Yeah, that's a good viewpoint. So there's one question from the audience saying Dieter has a problem with detecting small objects. Does the method based on DTR has the same problem? Does using cascade language solve this problem?
Yeah, that's a great question. So in our implementation, we actually zoom in images to avoid this issue, but that actually subsequently causes more memory consumption. So we're still looking into it. And for example, deformable data is under a way to tackle this problem. But overall, I think this is still open question. I think there are a lot of things in the future to be explored. That's a great question.
Okay. Yeah, I think that's all the questions from my side and the audience. So if you have any more questions, you can type. So Zhuowen will maybe stay for a little bit while, and then he can text, answer by text.
Yeah.
So let me play the
Thanks, Xiaolong. Yeah, thanks everyone.
Let me do the next talk. Basically, let me share. Where's my screen? Okay. So here's the next talk from Iro, and she's going to talk about a 3D scene graph and applied it to this structure to extract structure information. So let me just start.
Hello, everyone. In this tutorial, we want to see how to use graph-structured networks for learning purposes. But before we even look at these networks and how we can learn with them, we need to see how can we represent semantic information in a way that we can perform these learning purposes. And this is what I want to talk about today, how to structure the semantic information for graph purposes, for graph learning purposes. But before I even go into that, I want to give you a little bit of motivation that comes from a very practical application. I used to be part of the engineering team of a museum that was hosted in a very old building that dates back to the 1800s. And as part of the engineering team, we had to deal with very different processes that how to deal about the building. We had to care about the energy performance since there are multiple artifacts, historical artifacts that need to be preserved. We had to care about the structural stability of the building since it is an earthquake-prone zone. And we also had to care about asset management because there are many exhibitions and other as temporary and permanent exhibitions that are happening within the space that we had to care about. And finally, progress monitoring, because there are always some renovations going on or some new constructions within a museum. Now, for each of these processes, we would require to collect some as-is information about our building and represent it in a way that can be an input into these processes. Now, some examples of this information for these processes is spatial elements for the case of energy performance, structural, of course, building elements for the case of structural stability, and building elements both for the case of asset management and progress monitoring. However, as you can see, there's a lot of repetitive information that is going on in terms of the as-is information that is collected over different processes. And that is not something that only happens in this building. It's a universal challenge in all the built environment. And not only that, we need to have a representation of this information that, although it has to do with the same building, it ends up being in a very different format because its process has a very different way that it needs to be handled. So what if we could have a way to represent our built environment in a more general, ubiquitous structure that can then be fed into the different processes? And what would that information be? What information we need for the building and to perform different kind of processes? Well, that is what we call the as-is status of the building, and that has to do with what exists right now within the building. And what is defined in the literature as as-is status is a semantically rich 3D building model with attributes and relationships about building and spatial elements. But this is not important only for this industry. The architecture, engineering, construction industry is also important to other real-world applications. We are currently living in a physical world, but we are quickly transitioning into a hybrid one, where alongside us, we'll see virtual and augmented reality applications. Robots are going to live alongside us, and we'll see a lot of automation occurring around us. So what we would like to do is to have a physical world and digital representation in a way that is general for all applications. And from there, we can harvest application-specific ways to represent this information. We also would like the transition, the communication between the physical and the digital domain to be seamless. And on the one hand, we have to think that humans and other agents are going to interact with this information. So we need to structure it in a way that is interpretable by both humans and machines. And that is the motivation behind that work, 3D scene graph, which was presented back in ICCV 2019. But let's see a little bit more about the structure, this time from the computer vision lens. In computer vision, there are a lot of semantic data sets that exist out there that represent semantic information in a very specific way. We can have image labels, 3D parts, or action labels for videos. But every time we create a new semantic dataset, we ask ourselves, what structure or format should that semantic information have? And where should this semantic information be grounded? Let's start with the structure. Now, if you have this image of a space, you can represent the semantics of the scene with one label. In this case, it would be the word chair. You can also have information that provides, in addition to the object label, also the location of it, information about the location via a bounding box or a segmentation mask. You can also represent the scene with something that's a little bit more rich and descriptive, and that would be natural language captions, such as a brown chair on a blue patterned rug. And also you can use a structure that can be a little bit more structured than the free form of natural language captions, but also more rich than an object label and a bounding box. And that would be the 2D scene graph work by Risna et al., where you describe a scene based on the objects that exist within it. And then you have each of these objects have attributes, and there are relations between these objects, and all of them form a graph. Now, how about the space? We can ground information either on 2D space, in the 3D space, or in a combination of 2D and 3D. Now, if you do it just on 2D space, you are grounding the semantic information directly on pixels, which means a small change of the vantage point is gonna require you to either re-annotate the images or somehow be able to find a way to get this information from the first image to the second image so that you minimize this transferring, this re-annotation work. If you do it directly on the 3D geometry, you don't have the same problem anymore because if there is a change in viewpoint, you still have the same information grounded in the space in 3D. However, you cannot very easily acquire images from this domain, and given that a lot of applications in computer vision are in the 2D domain, this seems a little bit counterintuitive. So if we do both, if we use both the 2D and the 3D world, we are actually able to achieve the best of both worlds, right? So we can ground the semantic information on the 3D space, and then we can, whenever we want to use images, we can have them registered on this 3D space and project information back on them. So given these two findings about the what and the where of these semantic datasets, we came up with 3D scene graph. And we'll explain about the 3D scene graph right away. What is 3D scene graph? It's a 4-layered graphical representation about our world. The very first layer is that of the building, where the building is a node in the graph. Then there is a second layer that includes the space. So each space within this building, it's a new node in the graph. And then similarly, you have the objects that comprise these rooms that are also represented as nodes in the graph. Finally, we also add the camera as part of the graph, be that a static or a dynamic node that provides extra information about the visual status of the building. Now, these elements, as we discussed in the definition of the as-is status of a building, would require to have attributes. So each of these nodes can have a different set of attributes depending on the layer that they come from. So a building can have information such as its function or the area that it has. A space can have information such as the scene category or the volume of it, and object information, of course, up to the object category, as well as material or texture. And finally, for the camera, the standard camera parameters that one can require. But it wouldn't be a graph if there weren't any relationships, any edges between these nodes. And these edges can happen between nodes in the same layer. So just for example, querying if two spaces, what is the relative volume of two spaces? Or it can happen between across different layers. For example, if two objects belong to the same parent space, or if a camera is, or if an object is including another object given a very specific camera location. In order to demonstrate the structure of the 3D scene graph, we used the Gibson database, which has more than 500 buildings of indoor spaces of residential main use, but it doesn't have any kind of semantic information. So we needed to find a way to get this rich semantic information from the raw data of Gibson. And we were able to do that with a semi-automatic way that I will describe in a bit. But before that, I want to mention what this 3D scene graph addition of semantics to the Gibson database has. It has 3D mesh instance segmentation, 2D panorama instance segmentation, relationships between all the nodes, as well as rich attributes. Now let's see now about the semi-automated process that we can get this semantic information, the 3D scene graph essentially, on the Gibson database or any other 3D dataset. So the input to this method is a 3D mesh with registered 2D panoramas. And the output is a 3D and 2D instance segmentation of the input. Prior work that uses semi-automated methods to label, to annotate visual data, focuses mostly on the 2D domain. And whatever existed in the 3D domain relied heavily on human interaction. And for this reason, we came up with a way that uses high-level automation and limits the human interaction with the data. And we did that by leveraging existing 2D semantic detectors. And we looked at their performance, and we saw that there were some recurring errors. Specifically, if you look at the distribution of those errors, most of them are happening at the edges of the image, where the objects may not be 100% visible, as well as on objects that are too far away from the lens of the camera. And we wanted to improve this performance. That's why we built two robustification mechanisms that are able to address this decreased performance of the detector and address these errors. These mechanisms is the framing and the multi-view consistency. Now let's look at the framing. When you get a random frame, a random rectilinear frame, and you get the results of a 2D object detector, and in this case, we have the specific Gibson image that was that was passed through Maskar CNN, and the Maskar CNN was trained directly on the COCO dataset with no retraining or fine-tuning. Of course, in Gibson databases, we didn't have any kind of semantic annotations. And the results we're getting for this specific frame is that the couch is detected as a bed, and the table or bench of the kitchen is not detected at all. And both of them are at the edge of the image, are not very visible a lot, etc. But if we were to recenter those objects in the frame and repass them through the Maskar CNN, we are able to see that the detector is correctly identifying them and segmenting them. And that gives us an idea, because in our hands, we don't have rectilinear frames, but we do have panoramic images. So we can choose how to frame those rectilinear frames ourselves. And we use these two findings, that objects should be in the center of the frame, and the frame should be properly zoomed around the object, which means it should have enough context to understand what this object is, but it shouldn't be too small within the pixel number. We densely sample rectilinear frames in the panorama, where most of them are overlapping with something else. And we run all of them through Maskar CNN, we get the detections, and now we have to somehow aggregate this information, because for each pixel, we have more than one vote about the object that exists there. And we do that using a weighted voting scheme that takes into account the confidence score of the detector, as well as the distance of the segment for the frame center. But is this enough? When let's say we get this panorama that you see right now in your screen, you already see that the segmentation mask has some issues. This green mask corresponds to a table, and some of it is leaking onto the floor. Now we are to project this information on the 3D mesh, as you see on the middle of your screen. Then the labels of the table are leaking on other object surfaces as well. This can be due to errors in camera registration, object reconstruction, 2D segmentation, mask from the previous step, etc. However, we see that we are observing the same exact object from different viewpoints within the same building. So we can actually, and although each one of them on its own has the same problems, if we aggregate the information in a similar way as we did before with a weighted voting scheme, we're able to get the result that you see at the right side of your screen, where the table right now is not leaking on any other surface around it. And given that we now got the semantic understanding of the object labels and the instance segmentation, we can compute the rest of the attributes and the relationship for each of the nodes essentially that exist in the 3D scene graph. And most of them, we get them in an analytical way. Others, we have to do them on a manual way. And of course, where there are other learned methods that we can use, we use those. This is a result, the output of our 3D scene graph generation method. And you can see that each node represents a different object instance and color. Then you can see here all the attributes that exist, that the objects have, as well as the relationships that can be queried between objects given the specific camera location. In this case, you can get the spatial order of the elements, the occluding relationships between elements, or non-view dependent, essentially view independent attributes such as the relative volume. In order to evaluate the output of our method, we needed to have ground truth. And since the Gibson database did not have any ground truth, we used the output of the automated method and we verified it with humans in the loop, following the process that you see right now on your screen. And we evaluated the method that we proposed based on two aspects. First one is the performance of the detector. Do the robustification mechanisms actually help boost this performance? And of course, we also look at the user in the loop. Is it actually the method that we propose is faster than manual notation or not? But let's look at the performance of the robustification mechanisms first. And we see that instead of using the mask or CNN, the detector essentially on its own and project that information in 3D, when we use the framing and the multi-view consistency mechanisms, there is a substantial boost in the performance of the algorithm, both in terms of the average precision and average recall. And in order not to be biased towards a specific method, since mask-CNN was the best performing, we used the model of mask-CNN that was best performing on the COCO dataset. We wanted to use another detector that had a less good performance reported on the same dataset, on the COCO dataset. So we used BlitzNet, and it's a real-time detector, and we see again that the robustification mechanisms are able to provide a similar increase in the initial performance of the detector. So it means that it's not biased towards only one method, but it can provide the same kind of robustification and increase in the performance to every detector. Now, in terms of the time aspect, does it increase the manual notation speed or not? Is it even worth doing all this semi-automated process or not? We see that the use of the automated system does provide results about 7 times faster than if you were to annotate manually everything from scratch. But as we will see right away, even if you were to use only the output of the automated system, there is still practical quality to it, even without the verification step. And the first application that we will look at is that of predicate classification or else relationship classification. And we looked at 3 different relationships. The first one is that of spatial order. So given an image where we have the segmentation masks of the objects in the scene, without knowing anything about their classes, we are querying with respect to the query object, the one that you see right now on your screen as a yellow node. What is the relative spatial order with respect to every other node that exist in this scene? And so you can see here that there are objects that are to the front and right, to the back and left, etc., with respect to this query node. We also provide similar results for relative volume, where again, we follow a similar way of giving as input to the system segmentation masks that are agnostic to the class, and we get the results in terms of the relative volume. Finally, we have a model segmentation mask for the method where we provide as an output the occluded and visible mask of the object that is at the center of the frame. Again, this is class agnostic. There are many more things that and applications that one can think of given this 3D scene graph structure. The simplest that I can think of would be to just get the co-occurrence of objects. Specifically here, you can see the nearest objects to a microwave. And given that a microwave is most probably to be found within a kitchen, the closest object to it would be kitchen appliances. So yes, there is an oven that's closest to it, there is a sink, there is a refrigerator, etc. The same thing you can do for any other object that exists in the graph. And since we wanted to use the Gibson database, it would make sense to actually use this 3D scene graph within the Gibson environment. And this is actually another motivation for us to create this work, because one can now train autonomous agents that interact with the environments that exist in the Gibson database, but not in the metric space, but in a more abstract semantic space. Going forward, I would like to focus on introducing dynamic behaviors. And although there are people that have worked into introducing dynamic aspects into 3D scene graphs, I'm very interested, of course, in time and how spaces change over time, as well as humans and their interactions with the environment. I'm also very interested in the aspect of human-machine collaboration. Specifically, how can we reach 100% accuracy in tasks by leveraging both machines and humans, and which way is more optimal to do that, as well as to be able to understand which sources we can trust when we're building a 3D scene graph or any other kind of 3D semantic information graph for our buildings, because we collect usually information from many different sources. That could be multiple cameras within the building at many different times, from other sensors within the building. So which of those can we really trust and add them to this general, in one place located information about our 3D environment, about our building? And with that, I want to conclude this presentation. I want to thank my collaborators and you for listening, and I'm open to any questions. Thank you. Hello, everyone. In this
Okay, thank you, Iro, for the talk, and very, very nice graphics, and then very well presented talk. So if you have any questions, please type in the YouTube channel or the Zoom chat. So before, when you are typing the questions, so maybe I have one or two for Iro. So in the last part, you mentioned that you can use this representations for the autonomous agents. So what do you think is the right 3D representation for the autonomous agent? Like how does it exactly can be fit into the policy language, and how the agent can actually use this 3D representation to do better navigations or manipulation? Yeah.
Well, thank you, Xiaolong, for your question and for inviting me to speak. I think this is a great question, and I think it really depends on the task you are performing. But a lot of times, for example, in navigation, we do want to make the agent learn how to go to a certain room or to looking for a specific object. And when we do this in the metric space, we cannot really generalize to other environments. So I think that using a more abstract layer, this kind of semantic graph, can definitely allow the agent to learn the semantics of the environment, instead of a chair is 3 meters away from the table, but a chair is next to the table and is maybe located that way, etc. So that is the benefit that I see from having that. From my small experience with active agents, I have seen that it's very hard to learn the metric space in terms of generalization to unseen new environments. So yeah, that is part of the motivation why we did this.
Yeah, great. So speaking of generalization aspect, so since like the work is done in the Gibson environment, so I feel like the mesh there is relatively complete. So what do you have any comments on like how to extend this kind of work in more like if you just really taking Kinect cameras or some cameras on the robots, and then you look into the real world, and then seeing all the partial point clouds. How does it generalize to those kind of scenarios?
So I think there are two answers here. If we are talking about 3D scene graph prediction on these frames, then one can teach the agent to learn to predict them within the Gibson environment, because the semantics exist there, like the reducing graph annotation exists there, and you can annotate it and you can create a kind of noisy sensor with complete or incomplete data, and you can learn on that. Of course, there is the domain adaptation part, but hopefully it will be as close as possible to the reality, the learned task. If we're talking about the semi-manual, semi-automatic method, and how, if you applied that to different kind of data, how that would work, it's true that there are very specific, that there is some limitations to how it could be used, particularly since the specific panoramas were provided in a way that it gave maximum information from different views about the same object. One would think that if you have a stream that goes around into a space and observes the object from many frames, you would have to pick the most important ones, because otherwise you just overwhelm the algorithm and it's not going to really be able, it's also a loss of time, you're not going to be able to really get good results. So you would need to find something that we haven't done, and it would be a good extension to some other kind of data. How can you find the best views, the best panoramas, or the best frames to perform this semi-automated, this robustification mechanism?
Yeah, makes sense. Yeah, maybe not last question from my side. It's kind of a little bit open. So in this work, it's mostly how to do. It's very nice. You have a joint representation on 3D, and then the semantic side, the multi-view images, and then you can attach the semantic labels, segmentation labels to the 3D, and then you can actually use 3D to help you to prune and multi-view information to improve the semantics. So what about the other direction? So do you have any comments on like how can you actually help improve 3D reconstructions or getting better meshes from when you know more 2D semantic information? So can it be the other way around to improve 3D based on the 2D semantics?
Absolutely. I do think, and I think there have been a lot of works that look into the 3D reconstruction aspect by understanding semantics as well, either on online fashion or offline. Definitely understanding something about the class or on the geometry of the object or the material even of it could help in providing better reconstruction results at the end. So yes, even this kind of annotation, so the kind of semantic data set could be used for this purpose. Potentially I'm not 100% sure, I haven't thought of how the graph structure could help in reconstruction, but I'm sure there is definitely a way for a more structured approach to reconstruction as well.
I see. Okay. Yeah, sounds great. So I think maybe that's the first section of our tutorial today. So if you have more questions, please type in the chat or the YouTube channel. So we will take a break from now, and then we will come back at 11 a.m. Yeah. Okay. Thank you.
Hi everyone, my name is Yunzhu. Thanks for having me. Hi everyone, my name is Yunzhu. Thanks for having me here at the tutorial on learning representations via graph structure networks. I'm really excited to share some of my thinking and investigations in using graph structure neural networks for physical inference and model-based control. A little bit about me. I'm currently a rising fifth-year PhD student at MIT, co-advised by Professor Antonio Taroba and Professor Russ Tedrick. My research interests lie in the intersection between computer vision, machine learning, and robotics. In particular, I'm interested in enabling robots to better perceive and interact with the world via learning-based dynamics modeling and multimodal perception. Before coming to MIT, I obtained my bachelor degree from Peking University. I've also spent time at Stanford AI Lab at NVIDIA Robotics Research Lab. The main focus of this talk is to discuss why we want to learn a simulator from data and how we can use graph to capture the underlying inductive bias of the environments. We will also investigate how different modeling choices will affect the generalization power and their ability to facilitate downstream tasks in physical inference and model-based control. In recent years, we have witnessed a tremendous amount of progress in the field of robotics. In certain areas, robots start to become on par or sometimes surpass human performance. For example, the humanoid robots built by Boston Dynamics has clearly surpassed my personal capability by performing backflipping. Or in the self-driving domain, although we haven't seen a massive deployment of autonomous cars in our daily life, the field has moved a long way over the past few years. And in restricted regions, the car can sometimes perceive the environment better than humans by using multiple sensors and could potentially drive themselves more safely and comfortably than many human drivers. But what about complicated physical interaction with the environment? Has a state-of-the-art robot manipulator reached human performance yet? Let us see videos of humans performing various manipulation tasks, including creating an egg, spreading butter on a slice of bread, making dough and sushi. We can see from the videos, purely from observations of the environment, we can effortlessly perform a tremendous amount of manipulation tasks multiple sensors, involving rigid bodies and deformable objects. The ability to handle a wide range of objects and adapt to new tasks goes far beyond the reach of the current robot. The core for enabling these abilities is a mental model of the environment in our brain. We can reason about the compositionality of the underlying thing and predict how the environment is expected to change when we apply a specific action, which we refer to as intuitive physics. The predictive ability applies to objects of different materials, including rigid bodies, deformable objects, and fluids. Like what you can see from the video, the baby understands the physical interactions between the objects and can predict whether the tower will be stable or not after placing the cylinders one on top of another. And this intuitive understanding of physics allows the baby to make a stable tower. When compared with model-free reinforcement learning, using a learning-based intuitive physics model can give us better generalization ability and sample efficiency, which is also easier to specify the goal configuration. When compared with analytical physics model, the route of learning intuitive physics model can handle cases where the underlying dynamics are uncertain or unknown. Because we learn the model directly from observation, it is also better suited for partially observable scenarios. And you can see at the end of this video, the baby successfully made a stable tower. Let us make the problem more specific. Our goal is to solve the optimization problem by minimizing the objective function defined on the state and action over time horizon. The optimization is subject to two constraints. One is a dynamic constraint, which tells us how the state will evolve when taking the current state and the action as inputs. The other one is a policy constraint, which maps the current state to the action signal. The application domain we are considering is primarily on manipulation, where we want the robot to interact with the environment that contains diverse objects with different dynamics. There are three key questions we would like to ask when designing the systems. The first question is, what should be the state representations? The state of the overall systems consists of the state of the robots and the state of the environment. Determining the state of the robot is easy, and it is designed by humans, and we can add sensors to obtain an accurate state estimation. And the key challenge is how we should represent the environment. The second question is, given the selected state representation, how we should specify the dynamics model, and what model class we should use, and what it implies about the generalization ability of the learned model. Then, given the dynamics model, how we should solve the control tasks. During the talk, we'll have to constantly thinking about these three key questions, which lays the underlying principle of the modeling decisions. When determining a state representation, we draw insights from our everyday experiences. As you may remember from the example of a baby making a tower, compositionality is common in our daily life. Many ordinary objects contain repetitive subcomponents, ropes and soft robots, granular materials such as coffee beans, Lego blocks, or modeling clay. These objects are known to be very hard to model and control using traditional methods. In order to capture the compositionality of the environment and facilitate the generalization power of the system, we propose to use particles to represent the environment. As you can see from the images, different objects consist of particles, which indicates the object geometry as well as interactions within and between the objects. Particle as a representation is very general and flexible, which applies to objects of different materials, including rigid bodies, deformable objects, and fluids. Particle-based system also introduces the desired inductive bias for learning that the particles of the same type have the same dynamics within. To model the dynamics of the particles and their interactions, we use graph neural networks as the model class to learn the dynamics, where each particle is a node in the graph, and the interactions between particles are represented as directed edges. Here is a graphical illustration of the learning process. The graph contains 3 nodes and 4 directed edges. For each directed edge in the graph, we denote the sender as OI and the receiver as OJ. An edge encoder takes the information on both the sender and the receiver and outputs an edge representation denoted as EK. Then, for each node I, we aggregate all the edge representations on edges where the node I is the receiver. The aggregation is then combined with the information on node I and fed through a node encoder to derive the node representation. We can then define the loss function between the node or edge representation and the quantity we care to supervise the model. In our case, what we care about is the evolution of the state, hence the loss function is the mean squared error between the node representation and the actual state at time t+1. One thing to note is that we exploit the compositional nature of the system, where the node encoder is shared among all nodes, and the edge encoder is also shared among all edges. Thus, the systems can generalize to systems of different sizes or even outside the training distribution, as we will show later in the experiments. This formulation has also been the core of many foundational works in the direction, like interaction networks, neural physics engine, and graph structure learnable physics engine. In our work, we'll introduce some improved techniques on the base model to improve the modeling power. First, we use multi-step message passing to propagate the information multiple steps over the graph to capture the higher order interactions. Second, Since constructing a fully connected graph over the entire particle set is inefficient and quickly becomes infeasible when the number of particles increases due to memory limits, we build dynamic graph over the particle sets, where each particle will only connect to nearby particles that are within a certain distance. Since rigid objects are globally coupled, where a small perturbation on one corner of the object will instantly propagate to all particles within the object, we introduce the third augmentations that use hierarchical graphs for rigid and deformable objects. More specifically, we cluster the particle and assign an additional parenting particle as the roots of the cluster. The hierarchical design will enable a more efficient long-distance message passing within the object. Here we summarize the modeling choices we use for objects of different materials. As we discussed before, we use hierarchical modeling for rigid objects. In order to maintain the rigidness of the object, we predict a global motion for the entire object and back project the movement to each particle. For deformable objects, we use hierarchical modeling, but the motion of each particle is predicted individually to model the deformation of the object. For fluids, we use dynamic graph building where each particle only connects to nearby particles, and similar to the deformable object, each fluid particle will also have its own motion. On the right, we show our model's prediction results, where the inputs to our model are the initial positions and velocities of all particles. Our model can predict the long-term future and correctly capture the dynamics of the fluid and the interactions between the fluid and the rigid body. Here we show some more results on our model's dynamics prediction. This example shows two fluids falling down and merge with each other, where the left is the ground truth and the right is our model's prediction. The inputs to our model are the positions and velocities of the particles at the first frame. As can be seen from the video, the prediction is very close to the ground truth. Here is another example where we grip a deformable material using two cuboids, which are to mimic the two fingers of a parallel gripper. In this case, we assume that the gripper is fully actuated and the inputs to our systems are the initial states of the particles, where the left is the subsequent movement and the right is our model's prediction. Here we show another example of shaking a box of fluids. We assume that the container is fully actuated. Our model accurately predicts a long-term future by taking in the particle's states and the first frame and the subsequent actions for controlling the container's movements. As we have discussed before, all nodes share the same node encoder and all edges share the same edge encoder. Thus, our model can generalize to systems with more particles than during training. This example shows that our model can work in an environment containing 2 times more particles than training. The result is not perfect, but it is clear that our model captures the wave of the fluid particles caused by the container's movements. After we have obtained the dynamics model, how can we use it for control tasks? In this work, because the learned model is a neural network, which is naturally differentiable, where we can extract the gradients using off-the-shelf packages like PyTorch and TensorFlow. We can then use gradient descent to optimize the action signals and apply model predictive control framework to account for the modeling error. More specifically, here we use the blue dot to represent the initial state of the system. The goal is to achieve the target shown in red. We have an initial guess of the action sequence and use a learned model to predict the control outcome. We then define a loss function between the predicted outcome and the targets, and then backpropagate the gradients of the loss function with respect to the action sequence. We then iteratively update the action sequence to minimize the distance between the predicted outcome and the targets. The model may not be accurate enough, so we use model predictive control, where we only execute the first action U0, and then obtain the new state x1 from the environments. We then re-optimize the action sequence U using gradient descent to give the model an opportunity to adjust action sequence to account for the prediction error. Here we show our model's control results. The goal here is to shake the box of fluid. When the countdown goes to 0, we want the shape of the fluid to match the target shape shown on the top left. And here is the control process. And here's the result. Here's another example. The result is not perfect, but clearly shows that our model's dynamics prediction to help the controller to minimize the distance between the end state and the target. Here we show the control results in manipulating a deformable form. The decision variable of the control problem here are the position, orientation, and clipping distance of the parallel gripper. After 2 grips, the result roughly matches the target. Here's another example. We have also attempted to deploy our system into the real world by gripping these deformable materials to achieve the target shape shown on the top left. Here we show the control process. In order to estimate the particle positions from the perception data, we use a depth camera to scan the scene and fuse a point cloud to obtain a mesh of the environment. Since we know the table's height, we can clip the background to segment out the object, which is shown in blue on the top left. We then uniformly sample particles inside the surface of the object to obtain the current particle set for the model to control on. After 3 grasps, the resulting shape is closer to the targets, demonstrating our model's understanding of the dynamics can help guide the controller's action. Again, the results are not perfect, and there is still a large room for improvements of using a general-purpose robot to manipulate a deformable form into an arbitrary shape. Here we show 2 other examples of manipulating the form into simpler target shape. Here's a horizontal shape. Here is a tilted shape. We are not the only one who use particles to represent the states. There are concurrent work from Friends and Stanford who also uses particles to model the dynamics of deformable objects. There are also many follow-up works that scale the system to environments with much more particles or mesh-based systems and demonstrate stable future predictions of thousands of time steps. Here's a quick recap of what I just discussed. Again, our goal is to solve the problem shown on the left. And here are the 3 questions we are asking. We're using particles to represent the environments by using graph neural networks as a dynamics model to capture the compositionality of the environments. For policy search, we are using gradient descent and model predictive control to derive the control signals. The results are nice, but still, there are always limitations. One limitation of this work is that we have to assume the knowledge of the particles. So we are asking the question, can we learn the structure automatically from visual data? This is definitely not a simple task. Let us start from some basic examples. As you can see from the video, there are 2 balls moving around. You could realize that the balls are moving freely over the 2D space, bouncing back and forth between the boundaries, and there may not be any physical relationship between the red and the blue balls. But what about the second video, where the balls are starting from the same configuration, but you may realize that the 2 balls may be connected by some invisible physical relations, and the hidden confounding variables like relation type and relation parameters causally affect the ball's movements. And what about 5 balls? Can you guess the model? When you look closely, you may realize that there may be a rigid relation between the yellow ball and the red ball, and they always maintain a fixed distance with each other. The red ball and the pink ball are moving back and forth, and there may be some spring-like relation between them. Still, guessing the model is not trivial because there are latent connections you do not see that influence the movements of the balls. For example, they can be connected by rigid rod, spring, string, and so on and so forth. Notice that you could train a model for particular datasets to just learn the particular system. But what if I change the underlying graph and the latent interactions between the constituting components? They will cause trouble for the model to generalize. In many of these cases, you cannot memorize. You have to generalize to new latent graphs. In the ball environment, at least the node variables are visible. What about cases where estimating the node variables is hard? For example, manipulating and folding a shirt. Note that there are works in the field that show impressive performance in folding a shirt, but they typically only do the tasks for that particular clothes. What if you want to do it for general purpose garments like pants or full bodysuits using just one model? And the task can be even more challenging if we ask the agent to handle asymmetric clothes that are common in fashion shows. For me, it is hard to figure out how to get in and out of the clothes that are long fold. So in this case, we will have to resort to methods that can reason about the compositionality of the system and understand the causal relationships between different entities. If you use a single end-to-end model to learn the dynamics, you can try and fit to a particular systems, but won't be able to generalize. Another choice is to use encoder-decoder style models like VAEs, which represent each environment using a latent vector. But then generalization will be limited because there is no explicit modeling of the compositionality in the model, and it cannot generalize to systems that contains different constituting components than during training. Instead, we propose to encode the environment using a latent causal summary graph that explicitly reasons about the structure of the systems, which we hope can capture the underlying inductive bias and provide better generalization ability. The key is that we want to learn latent graph-based generative dynamics models, where a single model can handle cases with different latent generative graphs. Specifically, our proposed model, named Visual Causal Discovery Network, VCDN, contains three major components. The first component is a visual perception module, where we use an unsupervised key point detection algorithm that maps input images into a set of key points to enable node discovery. This is a completely unsupervised process and can be learned using an image reconstruction loss. The second component is a causal discovery module that infers the existence of the edges and the exogenous variables that govern the interactions between each pair of key points using graph neural networks. In the ball environments, the causal summary graph can represent different kinds of interactions, like rigids, springs, or spring. It also includes continuous confounding variables like stiffness or the rod length. The third component is a graph-based dynamics module that predicts the future conditioned on the inferred latent graph and the current states. Note that we only have supervision defined on the key point movements, and the model has to learn the inference and dynamics module jointly without direct supervisions on the causal summary graph. In other words, the model has to disentangle the relation types and estimates the continuous confounding variables in an unsupervised way. Here we show the evaluation results. In the ball environment, the first two videos compares the ground truth graph and the inferred graph. As can be seen in the videos, our model can successfully recover the underlying interactions. The fourth video shows our model's dynamics prediction when given just the first 10 frames as inputs. Our model can produce long horizon future prediction with a reasonable accuracy. Next, in the more complicated fabrics environments, where the ground truth is not even available, our pipeline can build a model of the tower by just watching its movements and deformations. The perception module finds a reduced order representation of the clothes represented using key points, and the inference module predicts a graph based on the key points that correspond to the underlying connectivity structure of the clothes. The same model, without any retraining or fine-tuning, can also model the structure of a shirt. The same model can also work for pants as well, where the discovered graph accurately describes the connectivity structure of the pants. What we now have, essentially, is the same model that can capture the fabrics of different dynamics in a causal sense that can generalize to different types of fabrics like towels, shirts, and pants. It can also adapt to changes in shapes like shirts with different sizes or different sleeve length, or the same type of clothes but with different physical parameters like stiffness. Moreover, because our model is based on graph structure networks, it can perform extrapolate generalization to systems that have different numbers of components than during training. For example, the bar plot shows the correlation between the estimated rest length of the spring and the ground truth. Again, we do not have the supervision from the ground truth interaction graph during training. However, the discovered continuous confounding variable have a strong correlation with actual physical parameter. The blue bar shows the result in environments that have the same number of balls as during training. The orange bar contains fewer or more balls than training, but the model still delivers reasonable accuracy in this extrapolation setting. The same thing happens for future prediction. As you can see from the right figure, the model trained on 5-ball environment shows a similar performance when tested on the environments with fewer or more balls. The baseline interaction networks that does not perform causal discovery on the underlying causal summary graph cannot generalize when encounter systems with different latent generative graphs. The modeling of the causal mechanisms in our systems also allows us to perform counterfactual prediction. It means that if you have a data point, we can ask what if questions like what would have happened if you change the rest length of the spring or the length of the rigid rod. We show results in both these cases using the box plot, where the y-axis is the mean squared error on future prediction. The purple region show results when varying the parameters within the training distribution, and the pink region shows result on variations outside the training distribution, which is on par with the in-distribution performance. The key message here is that causal discovery is vital for compositional generalization. It helps us understand the existence and types of interactions of the objects in the environment and enables more generalizable systems for dynamics modeling and physical inference of complicated visual things. There are follow-up works that build on top of these lines of idea and show their power in complicated robotic manipulation tasks. The last project I would like to discuss is the use of compositional dynamics model for visual question answering. As you can see from the video, objects of different color and shapes are moving on a 2D plane and bouncing into each other. The humans can reason about the interactions happening in the environment and answer 4 types of questions about the underlying dynamics. One is descriptive questions, like what is the material of the last object to collide with the science cylinder. The second type is the explanatory questions, like what is responsible for the collision between an object and another. The third type is predictive question, like what will happen next. And the last type is the counterfactual questions, like what would have happened if the science cylinder is not there. The ability to model the dynamical system is essential to answer these questions and require the model to capture the compositionality of the underlying thing. We build a pipeline that first use mask RCNN to perform instance segmentation and extract image patches from the input video. The extracted object-centric image patches are then fed through a dynamics predictor constructed based on graph neural networks to predict the evolution of the systems into the future. For a given video, we can predict the object's motion and collision events between them. When asked the counterfactual question, what would have happened if the gray ball is removed? We can simply remove the nodes that correspond to the gray ball from the graph and predict the future using the learned dynamics model. Let us see the original video again and guess the results by removing the gray ball. You may imagine that the science cube may going forward continuously and will collide with the purple ball. And this is exactly what the model will tell you when doing the counterfactual prediction. Next, we employ a neurosymbolic formulation of the model by using a question parser to transform the question into a program. And then use a program executor that takes both the derived program and the predicted object trajectories as inputs, and then produce the answer. We have shown in our experiments that the neurosymbolic formulation sets the gold standard and outperforms many end-to-end baselines. There are also related works that build datasets or environments that evaluate the agent's ability to perform reasoning in complicated physical environments. For example, Firay asks the agent to produce action signals to achieve a specific task goal, while Code5 assesses the capacity of the state-of-the-art models for causal physical reasoning in a synthetic 3D environment. In this talk, I have discussed the construction of compositional intuitive physics model for robotic manipulations, causal discovery and physical inference, as well as applications in visual question answering, where I have shown the use of graph structured networks with different types of scene representations, like particles, key points, and object-centric image patches. GNN captures underlying inductive bias, successfully model the compositionality of the systems, and deliver impressive generalization results. The lesson I learned is that the model is important. It can help the agent predict how the environment is expected to evolve when apply a specific action. It can be a critical component of the pipeline in robotic manipulation, physical inference, and tasks like visual question answering. Within the model, compositionality is a key for better generalization and is essential for reasoning about the complicated environment around us. And graph structure networks is a natural choice that delivers the desired inductive bias for learning. Before ending my talk, I would like to show these videos of humans manipulating diverse objects again. Humans are absolutely amazing, and I hope one day we would be able to close the gap between the robot and human performance. Thank you.
Okay, thank you. Thank you, Yunzhu, for the great talk and great work. So if you have any questions, please type in the channels or in the Zoom chat. So when you are typing the questions, maybe I can ask one or two. You in in the deformable object, the cloth and the shirt and the pants thing, is the topology and connection of the loads also automatically learn and discover there? Yeah.
Yes, thanks for the question, Xiaolong. Yes, the causal latent graph consists of two types of variables. One type of variable is discrete. That determines whether there is an edge between two constituting components. If there is, it also determines the type of that specific edge, which is basically a clustering process of disentangle the type of relationships. And conditioned on the discrete variable, it also produces continuous inference to estimate the continuous confounding variables that could potentially resulting from variations on, for example, resonance of the spring, stiffness, this kind of physical parameters.
Mm-hmm. Thanks. So you have very interesting examples on the asymmetric cloth. So how is it? How does the key point going to work there? So does it generalize from your training data without seeing the asymmetric cloth in test time? Yeah, it's able to get the topology right there as well.
Yeah, that's a goal. We haven't really going to that routes, although that's our like ultimate goal. Like we haven't really trained our system in a wide range of clothes that has different shapes. We currently only test on 3 types of clothes, like towels, pants, and shirts. So we are thinking like if we train it on a more diversified or programmably synthetic clothes, I do believe our system can generate to those scenarios.
Okay. So for the key point thing again, so as I remember correctly, the key point are also extracted well, with some self-supervised prediction or reconstruction tasks. So that works very well initially in human 3.6 data sets, and then some other data sets. So do you find it is able to generalize those key points, unsupervised or self-supervised key point discovery thing in more complex data? So currently it's also cloth, right? So when it goes to the video you just showed in the last slide, how is it going to generalize to those environments?
Yeah, there's a lot of actually a series of works on unsupervised key point detection from videos. We're just choosing the one we find works the best in our scenarios, which is based on work published by Kulkarni et al. I remember in 2018, somewhere around those. The general idea is to use image reconstruction loss and add bottleneck layers in the middle, such that the reconstruction or the decoder only gets a chance to look at a few points from the input image. And that's basically the most important points from the input image. And that is the key point positions that the model is finding. We find this works for cases where the background is static, at least for these specific scenarios. But I also know that there are follow-up works that tries to do the key point detections after like foreground and background segmentation that also delivers better performance in more diversified and complicated scenarios. And this is an active like research directions, especially generating these key points like for complicated things and also 3D things. And I also believe like this kind of like perception module, the advances in the perception module can be combined with our like causal inference framework to extend to more complicated scenarios.
Yeah, that's great. Maybe last question from me is, initially you have shown the particles, use the particles to represent fluid dynamics and those things. So we also see the DeepMind, they have some beautiful animations in their demo. But like you said, these all have some strong assumptions on these particles, and you extract the state already. You directly learn from the state. Do you have any thoughts on like how do you learn from vision from for these fluid kind of things? Yeah, so not just work on state.
Yeah, that's a very good question. And actually, the reason why our work and works from DeepMind works very well is because like we directly work on the state as you have just stated, and the state is clean. That means it learns from very clean data, and that's why it can generalize very well and roll thousands of steps into the futures and far beyond what it has been trained on. But in the real world, you have to consider there are definitely like some kind of perception noise you have to you have to handle from like visual perception data. In our case, we use the depth cameras to scan the object, obtain a mesh of the object and sample particles inside the mesh, which works for that specific objects, that deformable like squishy materials. But this also places an assumption, like the object has to be homogeneous. Like we didn't really distinguish like between like the types of different particles and assume all particles are of the same types. So I would think like going forward into the future, we will need some kind of visual prior that's observe a thing and tries to disentangle like the instances of different objects inside these environments, and maybe give us some initial proposal of the type and the materials of each one of these objects. And we can use this nerd like dynamics prior that help us infer like the specific type, specific physical parameters, such that the dynamics model can explain what it has been observed from visual perceptions. By going through this loop, I believe like this learning-based dynamics module has a very good chance of adapting to unseen scenarios that's or in scenarios where some kind of parameters are not directly observable, has to be inferred from this like observe and verify process.
Mm-hmm. Yeah, great point. Yeah, thank you.
Thank you.
So I think we can move to Lex, which is me. Yeah, thanks for the great talk again. Okay. All right. Let me move to my presentation. Okay. Hello, everyone. This is Xiaolong. I'm an assistant professor from UC San Diego. Today, I'm going to talk about learning long-term video prediction with graph networks. Sorry. Let me share again. So why do we need a prediction model? Here is a quote from the book of The Nature of Explanation. So what it says is that when we human is making a decision, we have a predictive model in our head, and we can use this model to simulate multiple actions and predict their possible futures. And then we can select the best action according to the prediction results. So in this talk, we are going to introduce how to allow machine to acquire this predictive model. Specifically, we want to train deep models for visual prediction. The task of prediction is, given a sequence of past observations, we want to predict the future observations. So why is the task interesting or useful? The first reason is that once we have a predictive model, we can allow the robot to perform model-based planning. The robot can just perform planning by enumerating multiple actions and select the best action before interacting with the environment. And prediction is also a very natural way to learn visual representations. While prediction is a very simple concept, a natural concept, there are different observations as inputs and outputs for the model. So one example would be pixel-to-pixel prediction. Given raw image pixel as inputs, the model will need to predict raw pixels as output. Here are some videos. The green boxes indicate the input frames, and the red boxes indicate the pixel prediction results. As you can observe, when predicting further into the future, like the street road, the quality of the image becomes worse because the uncertainty of the future becomes larger and larger a long time. And the pixel space is also very large for prediction. So it's actually a very, very challenging task. Instead of doing pixel-to-pixel prediction, in the fields of intuitive physics, we see a lot of work on predicting future states from input states. So here is an example on the modeling the complex dynamics of fluid dynamics and particle dynamics. These works rely on abstracting the object into particle states. However, in the real world, we do not have direct access to these states. Instead of focusing on the both extremes in this talk, we are tackling the middle ground to perform pixel to trajectory prediction. We argue that pixels are the primary way for the model to observe the visual world, but it is not a necessary thing to predict for planning. Instead of predicting every pixels, we predict how the object moves in the future without the backgrounds. So there are some previous work in these directions on predicting how the balls move according to physical rules and how the humans and cars move in the scene. But many of these works are still predicting a very short-term future, which is simple. In this talk, we are going to focus more on predicting long-term future, which is much more challenging. So the first work I want to talk about is our ICRR work on learning long-term visual dynamics with region proposal interaction networks. So there are several goals and applications for long-term visual dynamics prediction here. The first goal is when we are playing billiards on the left, we need to predict once the white ball is hit with a particular angle and force, how you will hit the following balls and the edge of the desk. The second goal environment or task is the fire dataset proposed by Facebook. The task is to place this red ball somewhere in this 2D space. And then we need to predict how the objects will move after the red ball falls down. So the goal of the task is always to make the green object touching the blue object. With the prediction model, we can plan how to place the red ball so that the green thing will eventually get in touch with the blue thing. If we see the previous work on visual prediction, it is mostly applied on predicting very short-term future, like the block falling down or the billiard ball to move just a little bit. Our hypothesis is that why there is a bottleneck in this is that how to get a good representation of objects for prediction is not very clear. And also, again, we just want to take visual input, but we do not have to predict the pixels. So let's see how previous work extract visual features from images. We focused on the work on using interaction network for prediction. The interaction network provides an object-centric representation, take the objects as a graph node and model the interaction between the graph node, the objects. In the visual interaction network paper, given an image input, they extract features for the whole image and use different channels in the feature map to represent different objects. And then they do interaction reasoning among these object features. The problem of this framework is that it can only has a fixed number of objects because the channel of the feature maps are fixed. And you also need to have fixed appearance and orders of the object, which is really not realistic for real-world applications. In the recent work on compositional video prediction, they first crop the object patch individually and then forward them to the convolutional network to extract object features for interaction reasoning. Because the object in here is model independent from the background, the representation does not really capture the context information. There are also works that try to first mask out other objects and then extract individual object-centric representation, taking the whole image as inputs. But then if there are 3 objects, you need to forward 3 times to the conflict, which is also very time-consuming. So motivated by the success in computer vision, especially in object detection, we find region-based features are actually very useful and powerful to encode the scene context and the object features at the same time. So this can allow us to build better prediction and planning models, which can also be generalized to multiple objects and more complex environments. We introduced the region proposal network for long-term dynamics prediction. We use the playing billiards as an example. Our model takes the RGB frames as inputs directly and predict the location of the future objects as the outputs. So our model contains 2 parts. The first part is the visual encoder, which extracts the object-centric feature. The second part is the interaction reasoning module, which takes the feature as input and model the interaction between the objects. We'll first talk about the visual encoder in here. We adopt hourglass Legward architecture as the encoder. We use ROI align or ROI pooling to extract each object feature given their bounding boxes directly from the image feature. Because we do ROI pooling on the image feature map, the region feature contains both the object states as well as the scene and context features. For billiard, it is particularly useful to contain the information, for example, on the boundary of the table. So in the second part of the model is basically the interaction Legward module. So there are three main components in the interaction module Legward. Taking these three billiard balls as example, the blue feature corresponds to the blue ball. We first have this self-dynamics corresponding to the Newton's first law, where we directly forward the object feature to a one-layer FC or multiple-layer perceptrons to encode the ball's own dynamics. We then model the interactions. We concatenate the feature on the blue board and all the other balls, including the red one and the green one. After concatenating each two features, we forward the concatenated feature into FC layer to encode their interaction feature. We then sum all the interaction features together to encode the blue ball's interactions with all the other balls. We finally aggregate all the both the self-dynamics and the relational dynamics together as the output for the interaction module. So the final feature is basically updated as after one interaction time steps between all the other balls. This pipeline of interaction is initially applied to the fully connected embeddings. In this work, since we are extracting the ROI feature, which is a spatial feature map, we can actually extend the interaction network to convolutional interaction network by replacing the fully connected layers with convolutional layers. So in this way, we can also capture the detailed shape interactions between the objects. Like in here is all just sphere or balls, but there can be situations where the object shape is a triangle or it's a rectangular shape. So then modeling the shapes and how objects interact with each other are also highly related to the shape of the object. And this is basically the overall architecture. For the model prediction, instead of doing directly pixel prediction, we are actually going to predict the location of the objects in the future. So during prediction, we combined the features from multiple time steps to predict the next time step feature. So the prediction is first happening in the feature space. This feature xit+1 is then forwarded to a FC layer for predicting the object location in time t+1 step. The loss function is essentially just an L2 distance between the predicted box and the ground truth box. We can apply this procedure recurrently to the future. In our experiments, so we basically have multiple data sets and environments we work on. The first environment is the fire data set, which has this rich physical interaction in here. And the task is to place this red ball in some places, and you need to predict how the balls are going to interact or how the objects are going to interact. And then you need to put the red ball in the right place so that the green one will touch the blue one. The second environment is the shape stacks. So it's just some cubes falling down. And then we also collected a new data set is called real billiard environment, where we just download from YouTube videos on how professional player is playing the billiard. And then we use this video to train the predictive model. We compare with several baselines, which are all related to the interaction network, but use different visual representations. So we basically find that here is some L2 distance and prediction errors from different models. And we basically find that our method is very much better than the previous approaches in different data sets, including the fire data set, the shape stack data set, and the real billiard and the simulation billiard data sets. And we also find the convolutional interaction network is slightly better than the interaction network. T-train here means the time steps we use in training. So in test times, because we can also apply our network recurrently to predict the future. So we can actually predict longer distance into 2 times of T-train steps. And then we show that in the sense of using it for generalization to further away in the future, we consistently do better than the baselines. In our experiments, we also predict, we usually perform predictions for 40 or 60 time steps in the future. So it's actually a very long-term prediction in here. So in the fire data set, there are usually 25 environments. And then there are 20 environments used for training and 5 for testing as a generalization environment. So we also perform the same kind of test that we test on the environments that is never appear in the training environment. And then in this kind of generalization test, we can see that our approach is still better than all the other methods. And the convolutional interaction network is also better than the interactional network. So, so these are just some numbers. So what is more impressive is our visualization for the results. So in here, we can see some predictions of the results. So we can see CVP's compositional video prediction. There's a mock mass baseline, and then our methods and the ground truths. So in here, we not only predict the object locations, but also predict the mask of the objects, essentially encoding the shape of the objects at the same time. And then we can basically see that our prediction is quite close to ground truth, even it is actually a very complex multiple object interactions, while the convolutional video prediction actually fails and the object kind of just penetrates across these environments because you encode the object representation independently from the environment. So it does not capture the context information in the CVP. Here is other results. So we can see our approach again is doing very complex interaction and still predict very correctly. We not only can predict how the ball moves, and we also predict the bar or the stick moves, how it can move into the future, while the both baselines just completely fail. And then we also do some visualization for generalization in here. So essentially, we can see that in this particular environment, so given the initial frames, we predict the future, just the first frame. And then we can see our method still generalized to this out of distributions unseen environment. And the baseline, again, is just getting very confused. Here are some more results on prediction in the real videos, and then we can have predict very long trajectories across the table. So going beyond prediction, our work in here also perform the task of planning. So eventually, given this predictive model, we want to apply to do something. So in here, we use this long-term predictive model to perform planning to solve this fire task. So the official task in this final fire dataset is the user need to choose the location and the size of the red ball to put in this 2D plane. So that after a sequence of interactions, the green object will hit the blue object. So in planning, what we do in here is just enumerating all kinds of possibilities of the initial location and the size of the red ball. And then we use our predictive model to predict the future. This will essentially generate multiple different videos given different initial ball and the location and the size. We then train a classifier given the video as input. And this classifier will output whether this task is successfully achieved. So it's just a video classification network, but it's classifying between whether you achieve the goal, the green thing is touching the blue thing, or is not achieving the goal. So given this prediction result, and input this to the classifier. If the classifier tells the video sequence is leading to the right future, then we select the corresponding feature as our solution for this kind of environment. So this is how we do the planning. We basically see that our method actually improves over the DQM baseline by a large margin. There are a few concurrent words as well we have not put in here, but we are still state of art in this FIRE data sets on planning where to put the red objects so that you can lead to the ideal results. So the previous work in the last paper only predicts the long-term future given one single action as the input. Like hitting the whiteboard in the billiard environment is just one action, and then you just wait for what happens in the next few seconds. So can we perform long-term prediction with multiple different action appears in different time steps? We introduce here our ICML work on compositional video synthesis with action graphs. Our goal in here is to learn a model that can be used to synthesize videos of actions. We want to have a model that can synthesize multiple actions and objects, support potentially simultaneously happen actions, and then coordinate them and the time and actions. So as shown in the right, we can have multiple objects moving at the same time. So how do we model this kind of actions? To achieve this, we basically construct an action graph representation where the nodes are the objects, the edges are the time actions. Specifically, each action here is annotated with a start and an end time. For example, if you can see the green large rubber cubes on the left, it is picked up and then placed back from this the 3rd second to the 5th second. So it's just basically timing it when it's going to be picked up and then placed back. Here is another example. So given the initial image frame, we extract their object features and construct the action graph nodes. In the action graph, we specify in the edges that from what time to what time the object is going to move. For example, in the upper part, we specify from time 1 to 5. We will basically have this red large rubber cone is going to contain the yellow objects on the top left. So given this graph and initial image, we can generate the videos on the right as the output. So you can see this also following that the red column is covering the yellow objects according to the graph. To schedule the actions, we can basically maintain time-specific action progress in different time steps. We record how much is the percentage of the action is done. So for example, a certain actions is initially just done 0%, and then 75%, and then 100% is done. Here is a brief introduction of our method. Similar to the previous RPIN model, the Region Proposal Interaction Network, we do not directly perform prediction in the pixel space. We first extract the object layout from the image and construct the action graph from it. We forward the layout map and the action graph to the graph convolutional network, which outputs the layout of the objects in the next time step. According to the new layout of objects in the next time step, we can warp the previous feature to a new image in the next time step. To do so, we basically use the optical flow map to warp the image according to the layout map. So we warp the time t-1 to time t according to the new layout in time t. We use the spaced image to image translator to refine the warping result and then get our final pixel output. So although in this work, we are predicting the pixels as the final output, but what really happened in between is actually predicting the object box and trajectories in the middle. The rest of the part is just doing image rendering according to the box results and the location results. So we perform our experiments in two data sets. One is the something data set, the other is the Kata data set. And then here are some results from the Kata data set. Then we can move multiple objects at the same time. Here are more results that we show just moving one object, but you can see that with different actions, we can basically have different outputs. Like, for example, in the first column, we have sliding the objects to different locations. And then in the third column, we have pick and place objects to different places. So the video is following what the action graph tells it to do. And here are some results from the something data set. Basically, we can just synthesize the future human actions by telling what the human hand should do. We should put down the object. We move the object to the right up in the or we move the object to the down left in the final column. So basically, we specify the action in the action graph, and then the pixels will basically follow the action graph. But what we have shown here is just some actions that is atomic actions. It's one simple action for each object. Can we use this approach to synthesize videos with a sequence of actions, so more complicated and longer term of actions that we actually want to see in this talk? So here gives an example that even though we didn't train for multiple actions in a sequence in training time, we can still generalize our model to do this. Essentially, there's a hand and a toy, A and B, in this scene. And then from the second to the third second, we are going to move the toy up. And then the next second is going to move it down. And then the next second is going to push right. So it's three actions happen sequentially in here. So let's see the results. So we can see it's moving up, down, and right, up, down, and right. So it's basically following the graph and then do the sequence of actions. And in the next example, we have A, B, C, D, two different hands, and then two balls in here. So what we do is we're going to have the left hand is going to push the ball to the right, and then the right hand is going to push the ball on the right to the left. So here is the prediction results. Basically, we can see that we can compose these different actions in different objects to generate these final videos. We can also apply multiple action in the same time steps. So essentially, we can combine the action together to form a new actions. So moving right and moving up at the same time, we basically move to the right and up direction. So here is basically some examples. In the first example, we can see right and up applying at the same time. So the hand is moving the cup to the right up, and on the second column is moving the cup, moving the object to the left down. And then on the third column, we can see that basically you have multiple coins at the same time, we contained the slit in the middle. So it basically becomes a huddle to the middle. So basically, we can have this kind of zero-shot generalizations into different combination of the actions for video prediction. So basically, that's all of my presentation today. Okay, that's basically all for my talk. And then so if there are any questions, you can post on the chat. And then I saw thanks Yunzhu for 2 great questions. So the first question is basically in the convolutional interaction network, is it possible to include some object priors telling the model that the objects are rigid, such that the objects won't be distorting or dissolving when predicting in the future? Yes, of course, but so I think currently in the RPIM model, we are extracting the ROI features of the object, and then the ROI feature also is concatenated through time. So by multiple times that the feature, I mean, ideally, the feature should learn to recognize whether it is a rigid object or deformable object. So but it's currently still completely learned from pixels and then using the feature. But it's a good suggestion. We can certainly encode something, encode more prior stairs, say this is a rigid object, and then we can apply rigid transformations when so also encode some rigid transformation as prior during interaction beyond just predicting Lex object feature. So maybe you can predict the transformation of feature to become the Lex feature instead of just happening in the latent space. So that might be one direction. And the second question is in the second word, the action graph. To what extent do you think explicit 3D modeling is necessary for accomplishing this task? The underlying physics is essentially 3D, and the idea is to extend the method from 3D modeling capabilities. Yeah, that's a great question. So currently it's all 2D, even the something is also 2D with just do ROI pooling, this kind of thing. So certainly it makes more sense to move in 3D. The first step is just when we are encoding the action, instead of saying moving the object to XY, it should be XYZ. So then you can encode more 3D from there. But right now, yeah, we didn't, because it's purely learned from pixel, we didn't have any 3D modeling there. We were worried that adding more 3D intermediate representation, I mean, depends on what kind of 3D representation you use. So if it is like explicit, like 3D mesh or shape, then you can accumulate some error when you are doing the 3D estimation. But if it is can be some latent, like recent work on deep voxels, so that could be a very good representation for the neural network to learn, and then or maybe some implicit function can be some future good 3D representation for this work. So yeah, this is our very good suggestions. So yeah, hope this can answer part of your questions, and thank you for the questions. So yeah, so I think that's all from my part. If you have any more questions, please type in the chat. I can answer you by text. From now on, if Hao is here, Hao Su is here, maybe Hao can present. You here? Okay, all right, he's here. Yeah, I think you can share and present directly. You're muted, by the way.
Okay, thank you. I'll share my screen.
Yeah.
Okay. Hello, everyone. Thank you for attending the tutorials. Next, I'm going to talk about graph neural networks for a different kind of perspective. I will focus on the compositional generalizability power of graph neural networks, especially when we use them to solve the vision-based policy learning problems. First of all, let us review the success of the machine learning framework. In the past decade, we have witnessed a lot of success for the machine learning framework, right? We've seen that we could use neural network to solve image classification or speech understanding or shape classification, many kinds of very important application problems. And these kind of problems are solved under the common framework, but we need a lot of training data and a lot of computing power. So we could roughly say that the success of those machine learning approaches are under the assumption that the training and the tested data are sampled from the same distribution. Or we could say that this is the in-distribution generalizability setup. So usually when we develop algorithm or do a theory and conduct a theory analysis, we assume a data distribution P. And then the training and tested data are both IID samples from this distribution. And at the training time, we will build a loss function. And this loss function compares the ground truth label and your prediction and penalize this kind of label by adjusting the learner's parameters. However, the world that we're living in really has combinatorial complexity. For example, we have all have the experience of playing certain kind of these kind of games like Lego, and we learn to build some simple structures and get familiar about like the basic manipulation skills, but then we are tested on building much harder like architectures. This is our experience from young, that what you learn may not be what you are tested. We have to face the real complexity of the world, which is combinatorial. How do we achieve the compositional generalizability? A very natural, well, it actually is also a way to form a natural curriculum that we learn from simple and test on hard ones. Recall our experience of taking all kinds of exams, right? Or preparing for the tests. Our teachers do not teach us to solve very complex problems at the beginning. Instead, we learn to solve some simple problems, like for here, the maze example, right? We learn about solving simple mazes, and then at the harder ones, we get a certain instinct of how to address the complex test type problem. Or for like learning physics, we learn about the basic, or we observe the phenomenon from the very basic interactions of very small number objects, like two objects or even a single object. And then we have summarized the rules, like Newton's rule, and then applied to build very complex architectures. So for this kind of compositional generalizability, we do need it to be implemented in machine learning context and help us to understand and interact with the complex world. I'm here talking about in a context of policy learning. For us working in computer vision, you may not be quite familiar with the policy learning, but basically you can think that it's kind of an interaction scale between the agent and the environment. And in particular, in the recent literature of visual-based policy learning, the common setup is, okay, we will learn a distribution, a policy distribution that allows us to sample an action based upon observation. So here, the pi A condition on S is what we desire to learn, which is a policy that might generalize compositionally. And here's a very concrete example. Like if we are playing the Pac-Man game, we hope that we're able to learn in a game a very few number of dots, but the learned skill can be generalized to a very complicated environment with many more dots. So how do we build a compositional generalizable policy? There are actually certain dependencies. Think that we first need the proper input representation. For example, for humans, we do have this kind of ability to some extent, okay? But we are based upon the reasoning that is like based upon objects. We will parse the environment to objects or somehow separate the space into regions and then build certain kind of graph or some kind of representation that allows us to reason about the interaction between the regions. So this, if we put in a Pac-Man context, is finding where the Pac-Man is and finding where the foods are, and then build a graph. And also we need certain kind of proper reasoning mechanism. For example, there are certain popular choices like graph neural networks or even transformers, which could also be thought as extension of graph neural networks. Some kind of mechanism that allow us to reason on the graphs. And this kind of perspective is also proposing, from at a higher level, a transition of paradigm from function learning to algorithm learning. Now, maybe let me be a bit specific. By function learning, I'm basically referring to the in-distribution generalizability, that from a lot of data, we fit a map from input to the output. Whereas for algorithm learning, we are kind of facing a more complicated scenario. For example, for the case of, of Pac-Man, as I just said, it's not only a simply like a fitting, but also there's kind of strategy in it. For example, if you build a Pac-Man learner, it could solve the Pac-Man through a greedy algorithm, or it might be a bit more aggressive in finding the minimal total travel distance. And this will correspond to solving the travel salesman problem, right? A harder problem. So you can see that if you represent the environment as a graph, then you're facing certain kind of graph algorithm learning challenge. And under this setup, your very fundamental assumption is different. Okay. You're assuming like you will have a probabilistic graph generation distribution. And this kind of a graph generation distribution is perhaps based upon the distribution over how the nodes are sampled, how the relationships are sampled, or some kind of way to specify from the perspective that there are certain reusable units. So for the learning task, it's also not as simple as like doing interpolation or extrapolation from training to test. Instead, you have to learn the computational units and the control flow. Maybe this is done on small graphs, and you want to see that the learned algorithm is able to work on the larger scale graphs or some new configuration of a computational units. Okay, so the test is through the recomposing the learned computational units, including the ability to control the algorithm running flow. Another more obvious way to contrast algorithm learning from function learning is think that when we learn about data structures or the analysis of our algorithms, we talk about like complexity, right? Algorithm complex, the computational complexity in terms of big O. When we say, okay, this algorithm is at this complexity of O and square or like exponential, right? This is a phenomenon that the complexity is dependent on the graph that you are processing with. It is determined at test time. This is a behavior very different from like the simple function learning we have been working on. How is it possible to use the graph neural network as a policy network? And this seems to be quite a natural practice. and has been studied in the past few years. For example, a very straightforward way is we will build an object-centric graph from observation. Like we may detect the objects of interest and treat every detected object as kind of a node of the graph. Maybe we could attach the image patch as the features of the node, or we could abstract in a certain way. And then we put interactions between the nodes and train a GNN to solve the task. Maybe we could even put certain kind of attention mechanism so that it learns better to focus on certain nodes or certain relationships. Okay. So if we build the graph neural network in this way, can we expect that it will generalize according to what we expected, like achieve certain kind of compositional generalizability? Now the answer to this question is yes and no. It's kind of a tricky question. Let me first show you some positive examples to illustrate the high-level idea and at least the promise of GNNs over other kind of networks, and then point out certain limitations and some frontier research directions. Okay, let me first show you the result on a game called multi-amnesty game. Okay. So here, you will have an image as the background. Maybe this image is certain kind of clutter, well, serves as the background, right? It could be sampled from like CIFAR or ImageNet. And on top of this image, we put a number of some numbers. It could be like 1, 2, 3 numbers. And you train the graph neural network to regress the sum of the numbers. Well, the tricky part is at the test time, we would like to put more numbers, like 4 numbers, right? Now, if you put more numbers, the problem obviously get difficult. Okay, so let us conduct some basic experiments. Okay, we have tried convolutional neural network, relational network, and some kind of a graph neural network. Here, ours refers to a variant of the graph neural network. And after we train the networks, we test them. We could test them on the graphs with 3 nodes or 4 nodes. And you could see that if we evaluate on the graphs of also 3 nodes, then, if we don't put it here, but the number is, this performance will still be high for all the networks. But if you evaluate it with the change of number of objects, then graph neural network shows certain kind of advantage. So this is already an evidence that graph neural network allows you to generalize better in terms like learning an algorithm to reason. Okay, and a second example is the experiment on falling digit. Okay, so this one I think I feel it's more interesting. Okay, this is a game designed inspired by the Terrace game. You have some numbers that are fixed and lying on the bottom of the figure. And then you have another digit that is falling from the sky. And because this is a policy learning problem, you have the privilege to control the falling object to move left or right. And your goal is to move this object along the falling process so that it will hit the one on the bottom with the scale most similar to it. For example, we have 8, 1, 8 on the bottom, but a 0 falling down, and then this 0 should hit the 1. So for here, you could also build a graph-based neural network and train and use it as the policy network for RL. Okay, so you could train it and test it on challenging scenarios. Like maybe at the test time, there'll be more digits in the figure. On the bottom, we see that we could put 9 digits. It can be shown that although this game is very difficult for CNN-based policies, for graph neural network-based policies, it's possible to learn. Okay, and if this is able to be solved, that means we actually, through the graph neural networks, we actually have learned certain kind of embedding that allow us to capture certain sense of the numbers, at least in the sense of comparing the numbers quality. So for the experiments I just shown, they show great promise of using graph neural networks as the policy. And in fact, there are also works before the experiments I just showed that that's about controlling the this kind of insect moving. You see that we can learn to control an insect with fewer number of like building blocks to controlling with the one with more complex structures. Okay, so the previous demonstration shows the promise of using GNN as a policy network. However, next I'm going to point out certain limitations of this perspective and perhaps suggest certain also certain possible directions to improve them. Okay. Okay. Now, because we have pointed out that the desired composition generalizability actually corresponds to an algorithm learning problem, let us do a certain kind of sanity check. Okay. So, do graph neural networks really generalize when solving the graph theory problems? And perhaps because we know the solution of the graph theory problems very well, we could use the comparison to imply certain improvement directions. Our experiments will based upon such kind of assumption that we will use graph neural networks to solve the graph theory problem at certain smaller scale graphs. And the test time, we evaluate this performance. We call this kind of a check the scale generalizability. Okay, let us pick two familiar algorithms, the shortest path algorithm and the travel salesman problem. Also, we make a simple assumption that the graph taken as input is a planar graph, weighted. So concretely, for the experiments I'm going to report, we will train on graphs with 30 nodes, but test on 100 nodes. And the metric is for like both the shortest path and the TSP, we will use the graph neural network predicted length to subtract the real length and then compute the ratio. So basically by the metric, 0 would be the best. Let us directly try to apply the GNN and the GNN with certain attention layer. And we show the metric, and you see that for the shortest path problem and the travel salesman problem, GNN performs okay, but not as expected. Okay, as I said, 100% 1 is the worst and 0 is the best. And you see that on the shortest path problem, weighted shortest path problem, the error, or relative error, is at 0.2 scale. Now with certain kind of attention, the graph neural network performance could improve. So there's a question, why not they scale up as expected? It turns out that they must have not learned the underlying algorithm, or even if they have learned the structural control flow, something is preventing to perform well. Okay, let me start the diagnosis from 3 perspectives. The first is we will check the perspective of the control flow. Okay. So we first point out that GNNs usually have a fixed number of layers. For example, we think about a very simple GNN that only has 2 layers. And then the information would be able to propagate to the 2 hop neighborhoods. Now, if you use this kind of a graph neural network to solve a problem with very large input graph with a very large diameter, and the underlying algorithm really needs you to process this large diameter. For example, for the shortest path, right, the receptive field of the graph neural network must fit with the diameter of the graph. And here, the receptive field of GNN, under assumption that the information only propagate to 1 hop neighborhood, corresponds to the number of layers of the GNN. Okay. So if we just test this 2-layer graph neural network on a large scale graph, it won't work. How do we deal with the problem? Well, natural observation is to align it with the while loop. Now think about the algorithm class. The graph algorithm we learned usually has this kind of while loop structure. Okay. So we will write down a while loop and then put a certain loop body, like the propagation of message, like in Dijkstra, right? We try to extend the solved region of the problem. And then we will also check certain kind of stopping criteria. We will check whether certain condition to stop will be satisfied. So if we translate it to language of graph neural network, then we should learn both a function corresponding to the body of the function and also certain stopping criteria. Unfortunately, for most of the graph neural networks today, they only focus on the body of the function that give it the ability to pass messages, but not the ability to learn a stopping criteria. Now, if we strictly follow this kind of logic, we can actually try to build a kind of new GNNs, which we call it the iterative GNNs. Like K is a index function about the number of layers that we have passed, or the number of iterations we have passed the messages. And H corresponds to the node and edge features. So we could do a for loop, and for every iteration of for loop, we will update the features according to the features in the previous iteration. And also we will update our stopping criteria, a stopping function. And this stopping function is actually also based upon the internal state of the graph. Okay. So let me introduce some of the caveats for this framework. First of all, okay, the HK corresponds to the node and edge features. They are updated at every iteration along the message passing. And secondly, the G function, which is the stopping criteria function, it will take the state inputs and predicts a confidence score. This confidence score is between 0 and 1, which is the confidence that we should terminate the loop. And if you read the form after the while, you could see that if at a certain iteration, the CK becomes very close to 1, then it will stop. The iterations will stop. And finally, we will return certain output. And this output is a linear combination for the internal features in the while loop at every iteration. And these internal features are weighted. Okay. So we will put, so this H function will be plugged in with other parts of this neural network so that we could train it in an end-to-end way through gradient descent. And you could also see that because H is a continuous function of the HJs and the CJs, the gradient passed to H will also backpropagate to both the CJs and HJs. So through gradient descent, we can automatically learn when to stop the iterations. For this kind of an iterative graph neural network, it allowed us to align the GNN with a while loop. So we could achieve adaptive and unbounded iteration. This is the first trick. Now let me introduce a second trick, which corresponds to the property of the specific family of graph theory problems. Okay. We observed that for many of the graph theory problems, they could be treated or viewed as homogeneous functions. By being homogeneous functions, we mean this. But still, we take our shortest path of problem solving as an example. Okay. Suppose that we're able to solve the problem for a certain graph. We will try to double the edge weights of the graph then we do not have to solve the problem again. We will just know that we will just use the same routing strategy, and the shortest path between any two nodes are just doubled. So from the perspective that we are learning, well, a function to compute the shortest path given a graph as input, this function is a homogeneous function, or more precisely, a positive homogeneous function. This f is the shortest path computing algorithm, and f lambda x, where x is the weights on the graphs, equals to lambda times fx. Okay. So if we are able to inject this kind of a prior into the graph neural network, theoretically, it should help us to learn the shortest path. So then there's a question that is raised: how can we build a universal homogeneous function approximator? It turns out that there's a very simple way. Think about the MLPs or CNNs that we're using every day. These networks basically have a structure of having a composition of the linear layers and the ReLU layers. But for the linear layers, they are actually affine layers. Right? There's a bias term greater than 0. Now, further inspection shows that ReLU itself is the positive linear function, a positive homogeneous function. This will scale the input of ReLU, then the output of ReLU will just scale by the same magnitude, if the scaling factor is positive. And as long as we remove the bias terms in MLPs, the composition of ReLU and this new pure linear transformation becomes a positive homogeneous function. So this is a simple inductive prior that we can add, which is very effective, as I will show soon. Okay. And there's a third perspective, which is corresponding to the loop body. Okay. So suppose that we're still talking about the shortest path problem, and then one iteration of the GNN could correspond to one iteration of the Bellman-Ford algorithm. Now, in the Bellman-Ford algorithm, what do we do? At every step, we will do the operation that I'm showing on the left. I'm showing on the left, right? So basically, you try to compare the current recorded distance with the possible distance propagated from its neighborhoods, where dist I or j are so far the shortest distance to reach a current node from a certain source node, and wij is the weight. And for our graph neural network, we can actually make a very straight analogous. So for the dist I or j, they could be viewed as the node features, whereas for the wij, they could be viewed as the edge features. And then here, the Bellman-Ford update equation is actually telling us what kind of pooling function that we should use. Okay. So this mean in a Bellman-Ford algorithm should be translated to the kind of max or min pooling in designing the graph neural network. How much does this kind of choice of pooling layer matters? Now, this is the analysis from a ICLEA paper this year. Okay, well, we can try to build a graph neural network by replacing the pooling by min pooling or sum pooling. Now, we test the performance on interpolation and extrapolation experiments. By interpolation, we mean that the train and test graphs are of the same size or the same number of nodes. Whereas by extrapolation, we mean that the test graph can be bigger, or you can directly change the weight on the graph to make the weights larger, and it requires extrapolation. And you could see that for like the interpolation experiment, the performance of using sum pooling is still okay. However, when it comes to the extrapolation setup, like if the test graph is more nodes than the input in the training graphs, and then mean pooling is very important. So this shows the importance of aligning the loop body structures. Now, all in all, we have this kind of observations of designing graph neural networks inspired by like the underlying algorithm to run. And we see if we apply all the revisions together, like we introduce the iterative structure, learning to stop, and then we make the layers homogeneous, and then we also use the mean or method pooling, we can actually greatly improve the performance of the shortest path or the travel, even the travel salesman problem. You can see that on the shortest path problem, we get almost perfect performance. And even for the travel salesman problem, which is an NP hard problem, we can get quite reasonable results. Okay, so these are the lessons that having the algorithm alignment between your GNNs and the desired algorithm is important. Another way we could say, when we are designing the GNNs, we are imposing certain kind of weak prior or algorithm family assumptions. And then we learn to discover the family, the right algorithm in a family. Okay, so in the end, I'd like to put some of the related works. And in fact, there are many discussions into this kind of problem in the machine learning community and robotics community as well. We see that there are certain works that studies the structure policies, and then there are also the more recent works to further investigate the graph neural networks for like solving this kind of graph learning problems. Okay, and there's a final piece of note. While the algorithm alignment allows us to generalize or compositionally generalize for some graph theory problems and could be applied to the policy learning problems, it's still not a universal graph theory problem solver, especially if the number of iterations needs to be very deep. Now, there's a thing about example, if an algorithm has to be solved with complexity O n raised to the third power or even higher order of polynomial, then you need a very deep network. And gradients to penetrate through these many layers becomes very hard. To give a concrete example, now if we want to solve the Bomberman problem, okay, which includes more sophisticated mechanisms, this becomes a lot harder compared with like the Pac-Man I just shown. And even if we give the algorithm alignment, we try to solve the minimal spanning tree using a classical algorithm, this is very difficult. On the other hand, if you want to solve by the prim algorithm alignment, then this becomes much easier. Okay, thank you very much for listening. And here are my updates.
Thank you. Thank you, Hao, for the talk. So there are two questions in the chat from Yunzhu. So the first one is, how does the specific structure of the graph neural networks influence the generalization performance?
Yeah, I guess after I introduce in the second half, maybe Yunzhu already get a sense. Obviously, this really matters a lot.
Okay. And then do we have to make assumptions on the maximum degree that a node can have when doing the test time larger scale testing?
Yeah, this is a great question. Okay, if we are using like the mean pooling or method pooling, right, and we are having this iterative process, then we have built the alignment between the train and test graphs. And according to our experience, we do not need assumption on the degree of node.
Mm-hmm.
Which, yeah, okay, aggregation function. Yeah. This is also answered.
Okay. Yeah, so maybe I have one question in the on the first part is like So your policy learning is building up this graph representation. So when
Right.
you are learning the policy, are you backprop the policy gradient to tune the graph representation as well, or is the graph representation
right.
changed according to the
Right.
task? Yeah.
This is an excellent question, which is actually also a deeper question. It actually is relevant to what kind of policy learning framework you're using. For example, if we're considering like, if we are considering like on-policy learning algorithms, and basically the major job for the policy is not to, like, we are like, okay, sorry, let me rephrase. First of all, you could try to think to use a GNN to build a policy network, but more precisely, there's a distinction of whether you're using the GNN to build a policy part of the network, or you could also use GNN to learn the value network. Now, if you're using the GNN to learn the value network, then this GNN must scale well, and the gradient will have to penetrate for predicting the value. Okay. On the other hand, if you're just using the GNN to build a policy network, even solving the same problem, the requirement for the GNN could be actually simpler. Because think about the Pac-Man example. The Pac-Man example. Oh, sorry. Like the Pac-Man is a greedy strategy, right? If my goal is to learn a greedy policy, not shortest path or TSP, then you could just find the dot that's closest to you, right? Which means that if you have a graph neural network, you just need like one hop information at one hop. Just the one layer of GNN works. Now, if you're using the GNN to build like the value network, okay, that's much harder. Yeah. So it actually really depends on how you will plug the GNN into your high-level learning framework. How do you verify that the GNN architecture is aligned apart from hand engineering the architecture? That's another great question. So far, the research are more from a theoretical insight perspective. Okay, now we are pointing out the importance of the alignment between architecture and the desired underlying algorithm. However, really, how to achieve this kind of alignment, this is a tricky question. Like maybe attention helps us, maybe architecture search helps us. Okay, maybe there are also other approaches like meta learning allows us to select the good assumption help us. But I believe that it's really a good research question for the future. Yeah, and in terms of verification, I personally feel that scale generalizability is already a very good evaluation criteria. If you are using the in-distribution generalizability, you can see that as long as you provide a lot of data, it's possible to hack. However, if you use the scale generalizability, the space for overfitting the training data gets a lot smaller.
Okay, thank you. Any more questions? Okay. Yeah, we are a little bit out of time, but great talk. So if you have any questions, you can email us. And I think we can end here, but since this is already synced to the YouTube live stream, so the video will be just always be there. So you can revisit. I mean, I will edit a little bit maybe, but the whole thing will be online basically. Yeah, thank you all for attending the tutorial, and I think that's all for today. Thank you.